Hello there, and welcome to Physics with William. I'm thrilled to have you here with me today as we embark on a fascinating journey into the world of science. Here we don't rush through concepts, but rather take our time to really explore the depth and wonder that physics has to offer. Whether you're a casual observer or a dedicated student of science, this space is meant to provide a calm yet insightful look at the universe around us. Now today we're diving into a question that, while it might seem simple at first, holds a depth of complexity that has puzzled scientists for centuries. We're talking about charge. You've probably heard of it before, maybe in the context of electricity or magnetism. But what is it really made of? What exactly is charge? How does it behave and why does it matter? This is a question that cuts to the very heart of how the universe operates at its most fundamental level. You might be wondering, what time is it where you are? Or, where are you listening from right now? Funny how something like time can be so elusive, much like our understanding of charge. We often think we know it, but when we stop to really think about it, it becomes a bit more mysterious. So, wherever you are and whatever time it is, I invite you to slow down for a bit and think deeply with me about something that shapes everything we know: charge. If you find this video interesting, soothing, or just a nice way to unwind, I'd be so grateful if you gave it a like and maybe even subscribe to the channel. It helps bring more curious minds into this corner of calm and exploration. With that, let's jump right into our topic and see just what we can discover about charge, a fundamental concept in physics that influences everything from the smallest particles to the vast reaches of the cosmos. So, sit back, relax, and let's explore together. Charge is a concept we encounter regularly, whether we're talking about the electricity that powers our homes, the magnets that stick to our refrigerators, or the devices in our pockets. Yet, despite its omnipresence in our daily lives, the true nature of charge remains a profound mystery in physics. To understand what charge really is, we need to take a step back and consider its place in the universe. At its core, charge is a fundamental property of matter, much like mass. Just as mass tells us how much matter an object contains, charge tells us how an object will interact with electric and magnetic fields. It's a property that can be found in the building blocks of the universe, particles such as electrons, protons, and other subatomic entities. But while mass is relatively easy to grasp, an object with more mass is heavier, and an object with less mass is lighter. Charge is far more elusive and doesn't fit as neatly into our everyday understanding. The first thing that stands out about charge is that it comes in two varieties: positive and negative. This division gives rise to the most basic law of charge: opposite charges attract, and like charges repel. You've likely seen this principle in action if you've ever played with magnets, where two north poles or two south poles push away from each other, but a north and south pole will stick together. Similarly, an electron, which carries a negative charge, is attracted to a proton, which carries a positive charge, while two electrons, both negatively charged, repel each other. The interplay between these positive and negative charges shapes much of the world around us, from the structure of atoms to the flow of electricity. However, charge isn't as simple as just these two categories. The more we look into the concept, the more we realize that charge, in its true form, is much more complicated than a simple push-pull dynamic. For example, how do we define and measure charge? How do we quantify it? And what, exactly, is the mechanism behind its behavior? These questions take us deeper into the world of physics, and the answers lie in understanding the nature of electric and magnetic fields, as well as the forces that govern them. The concept of charge has a rich history, beginning with the ancient Greeks, who first noted the effects of static electricity. The word electricity itself comes from the Greek word electron, which means amber, because ancient Greeks discovered that rubbing amber could produce static electricity. Over time, scientists like Benjamin Franklin and Michael Faraday made breakthroughs in understanding the relationship between electric charges and forces, it became clear that charge was something deeply embedded in the fabric of the universe. But even with all the advancements in our understanding, charge itself remains somewhat of a mystery. In the 19th century, the work of scientists like James Clerk Maxwell helped us understand that electric charge is not just a static property, but one that is dynamic and interconnected with magnetic forces. Maxwell's equations, which describe the behavior of electric and magnetic fields, revealed that these fields could travel through space, carrying energy and influencing the movement of charged particles. This discovery laid the foundation for much of modern physics, including the development of technologies that have revolutionized our lives, from radio waves to wireless communication. Yet, even today, charge defies a simple, intuitive explanation. It's one of those concepts that, while we use it daily, remains frustratingly abstract. What, after all, does it really mean to say that a particle is charged? What is the essence of charge? Is it a tangible substance, a property of matter, or is it a fundamental aspect of the universe itself, one that we will never fully grasp in terms that our minds can easily comprehend? In the realm of quantum mechanics, things get even stranger. At the quantum level, particles don't behave in ways we can predict with absolute certainty. Instead, they exist in probabilities, existing as clouds of possibility rather than fixed points in space. And yet, despite this inherent uncertainty, charge remains a defining property of these particles. Electrons, for example, consistently carry a negative charge, while protons carry a positive charge. But these particles aren't solid objects in the traditional sense. They are quantum entities with properties that depend on their interactions with other particles and fields. The fact that charge remains a constant property despite the strange behavior of particles in quantum mechanics suggests that charge, in some sense, is not just a feature of particles, but something more fundamental, something that transcends our current understanding of matter itself. As we dive deeper into the world of charge, we'll begin to see that it's not just an isolated property of particles. Instead, charge is intertwined with the very structure of the universe. It's part of the fabric that holds matter together, dictates the behavior of light and electromagnetic radiation, and governs the forces that shape the cosmos. To truly understand what charge is, we must look beyond the simple push-pull interactions we observe in everyday life, and explore the underlying forces and fields that give rise to this fundamental property. Charge, in this sense, is a gateway to understanding the forces that govern our universe. From the smallest subatomic particles to the vast reaches of space, charge is the invisible force that shapes everything. But its true nature is far from simple. In fact, the more we learn about charge, the more we realize that it's tied to some of the deepest mysteries in physics. What exactly is charge made of? How does it behave in the quantum world? And what role does it play in the grand scheme of things, from the interactions between particles to the structure of the cosmos itself? In the end, charge may not be a thing we can easily touch or measure in the way we can measure mass, but it's a property that underlies the very nature of the universe. As we continue to explore the mysteries of charge, we'll uncover deeper layers of understanding that not only illuminate the nature of charge itself, but also reveal the interconnectedness of all things in the universe. So, while charge may be one of the simplest concepts we encounter in our study of physics, it's also one of the most profound. It's a reminder that the universe is far more intricate and mysterious than we might ever fully understand, and in that mystery, there's a beauty that invites us to continue exploring, learning, and discovering. To understand charge at a deeper level, we must first turn our attention to the building blocks of matter itself. The most fundamental particles we encounter in the world of charge are the electron and the proton. These two particles, while vastly different in terms of their mass and role in atoms, are the primary carriers of charge and the ones that shape the nature of electrical interactions. Let's start with the electron, a particle so small that its size is almost immeasurable, and yet its effects are felt everywhere. The electron is a fundamental particle, meaning it is not made up of smaller components. It carries a negative electric charge, which is the basic unit of negative charge in the universe. Electrons are found in the outer regions of atoms, where they orbit the nucleus, a dense centre made up of protons and neutrons. While we often think of electrons as being similar to tiny balls or particles zipping around the nucleus, the truth is a bit more complicated. In the realm of quantum mechanics, electrons don't have a definite position in space. Instead, they exist in what is known as a probability cloud, a region around the nucleus where they are likely to be found. This behaviour is due to the wave-like nature of electrons, a concept that is central to quantum theory. Despite their small size and mysterious behaviour, electrons are critical in determining the chemical and physical properties of matter. They are responsible for the formation of chemical bonds, the flow of electricity, and the interaction of atoms with electromagnetic radiation. The movement of electrons through a conductor, like a wire, is what we call electric current. In essence, electrons are the charge carriers that allow for the transmission of electrical energy across distances. Now, if electrons carry negative charge, then what about the counterpart, the proton? The proton, like the electron, is a fundamental particle. It carries a positive electric charge, and together with the neutron, it forms the nucleus of an atom. Protons are much heavier than electrons, with a mass approximately 1,800 times greater. Unlike electrons, protons are not found orbiting the nucleus. Instead, they are tightly packed in the centre of atoms, where they contribute to the overall mass of the atom. Protons, however, do not move as freely as electrons. The positive charge of the proton attracts the negatively charged electrons, keeping them in their orbits around the nucleus. The existence of both electrons and protons, each with their respective charges, gives rise to one of the most fundamental principles of nature. Opposites attract. The negative charge of an electron attracts the positive charge of a proton, and this attraction is what holds atoms together. If it weren't for this interaction, atoms would not form, and matter as we know it would not exist. The balance between protons and electrons within an atom determines the atom's overall charge. If an atom has the same number of protons and electrons, it is electrically neutral. However, if there are more protons than electrons, the atom will have a positive charge, and if there are more electrons than protons, it will have a negative charge. The behaviour of protons and electrons is governed by the electromagnetic force, one of the four fundamental forces of nature. This force is responsible for the attraction between oppositely charged particles and the repulsion between like charges. The strength of the electromagnetic force is determined by the magnitude of the charge, with larger charges exerting a stronger force. In addition to this attractive force, there is also the concept of the electric field, which is a region around a charged particle, where other charged particles will experience a force. The electric field generated by a proton, for example, will influence the behaviour of nearby electrons, pulling them towards it. Similarly, the electric field of an electron will repel other negatively charged particles, which is why electrons tend to stay away from each other. While protons and electrons are the primary carriers of charge in most situations, they are not the only ones. There are other subatomic particles such as neutrons, neutrinos and quarks that also interact with the electric fields and carry various types of charge. Neutrons, for example, do not carry any charge at all. They are electrically neutral, which is why they do not participate in the same types of interactions as protons and electrons. Quarks, the building blocks of protons and neutrons, carry fractional electric charges, and their interactions form the foundation of nuclear forces. The properties of protons and electrons, however, remain the most important when it comes to understanding charge in the context of everyday life. The fact that protons carry a positive charge and electrons carry a negative charge gives rise to the most fundamental interactions in the universe. These interactions shape everything from the behaviour of atoms to the formation of molecules, the flow of electricity, and even the light we see. One of the most interesting aspects of the electron and proton relationship is their balance within atoms. This balance is not just important for the structure of matter, but also for the stability of the universe itself. Without the attractive forces between electrons and protons, atoms would not hold together and chemical reactions could not occur. This interplay of attraction and repulsion is the foundation of all matter. It dictates the properties of materials, governs the behavior of molecules, and even plays a role in the formation of stars and galaxies. The relationship between protons and electrons also plays a critical role in the generation of energy. In chemical reactions, particularly in the case of oxidation and reduction, electrons are transferred from one atom to another. This transfer of charge is what allows for the release of energy. For example, in the case of burning fossil fuels, the energy released comes from the movement of electrons between atoms as they bond and break apart. The same principle applies to the functioning of batteries and electrical circuits, where the flow of electrons through a conductor creates an electric current that powers our devices. But while we've spent a lot of time discussing the proton and the electron, it's important to remember that these particles are not independent of one another. They exist as part of a larger system, a system that is governed by the rules of quantum mechanics and the interactions of electric and magnetic fields. The behavior of individual particles, such as the proton and the electron, is influenced by the presence of other particles and the forces that act upon them. For example, the way an electron behaves in an atom is not only influenced by the proton in the nucleus, but also by the other electrons in the atom. These electrons interact with each other, sometimes attracting and sometimes repelling one another, creating a complex web of interactions that determines the overall behavior of the atom. In addition to their roles in forming atoms, protons and electrons also play a critical role in the formation of electromagnetic fields. These fields, which are generated by the movement of charged particles, influence the behavior of other charged particles and are the foundation of electromagnetic radiation, including light. The interactions between charged particles and electromagnetic fields are what make technologies like radio, television, and cell phones possible. When electrons move through a conductor, they generate a magnetic field that can interact with other magnetic fields, creating a complex network of forces that underpins the world of electronics. So while the proton and the electron may seem like simple particles at first glance, they are anything but. They are the building blocks of matter, and their relationship forms the foundation of the physical world. Their charges govern the behavior of matter on every scale, from the subatomic to the cosmic. The interactions between electrons and protons are what hold atoms together, form chemical bonds, and generate energy. Without them, the universe as we know it would not exist. Their behavior, governed by the fundamental forces of nature, is what drives the most basic processes of life, technology, and the cosmos. The electron and the proton may be small, but they are essential to everything around us. Charge is often described as a fundamental property of matter, but what does that really mean? To grasp the nature of charge more fully, we need to understand that it is not merely a characteristic of individual particles, but also the origin of one of the most important fundamental forces of nature, the electromagnetic force. This force governs the interactions between charged particles, and it is one of the four fundamental forces that shape the universe, alongside gravity, the strong nuclear force, and the weak nuclear force. In this chapter, we'll delve deeper into what charge really is and how it gives rise to the electromagnetic force that affects everything from the smallest subatomic particles to the largest cosmic structures. At its most basic level, charge is a property of particles like electrons and protons, as we've already seen. But it's not just about the individual particles themselves. Charge defines how those particles interact with one another. This interaction is governed by the electromagnetic force, which is one of the most powerful forces in nature, responsible for almost all phenomena we encounter on a daily basis. It is the force that holds atoms and molecules together, that causes electric currents to flow, and that governs the behavior of light. To understand charge fully, we need to understand how this fundamental force works. The electromagnetic force is unique in that it has two distinct effects. It can attract or repel particles depending on their charges. If two particles carry opposite charges, they will experience an attractive force. This is why protons and electrons are drawn together, forming the basis for the structure of atoms. On the other hand, particles that carry like charges, two protons or two electrons, will repel each other, pushing away in an effort to minimize the energy in the system. This repulsion is why electrons, for instance, do not collapse into the nucleus of an atom, but instead orbit the nucleus in a stable configuration. This ability of charge to create attractive and repulsive forces is a hallmark of the electromagnetic force. The force is not just confined to small particles, it extends across space and influences objects at much larger scales. For example, the electric field generated by charged particles can extend across distances, influencing other particles or objects in its vicinity. This is the reason why you can feel the effect of a charged object, even when it's not in direct contact with you. It's the same force that powers electrical devices that enables us to generate light and heat, and that affects everything from the chemical reactions in your body to the way stars shine in the sky. In fact, electromagnetic interactions are so important that they are responsible for much of the structure and behaviour of the world around us. Take, for instance, the chemical bonds that hold atoms together to form molecules. These bonds are a direct result of the electromagnetic force between electrons and protons. The attraction between the negatively charged electrons and the positively charged protons in different atoms allows atoms to stick together, forming molecules. Without the electromagnetic force, there would be no chemical reactions, no life, and no material world as we know it. The strength of the electromagnetic force is immense. In fact, it is far stronger than gravity, though gravity is the more noticeable force on larger scales. A single proton and electron experience an electromagnetic attraction that is about 10 to the power of 36 times stronger than the gravitational force between them. Yet, despite its strength, the electromagnetic force behaves differently from the other fundamental forces. While the gravitational force is always attractive, the electromagnetic force can be both attractive and repulsive, depending on the charges involved. This dual nature of the electromagnetic force makes it unique and much more versatile than gravity. One of the fascinating aspects of charge and the electromagnetic force is the concept of the electric field. The electric field is an invisible force field that surrounds a charged particle, extending outward from the particle and influencing other charged particles nearby. If you've ever rubbed a balloon on your hair and stuck it to a wall, you've seen the electric field in action. The balloon becomes charged by the rubbing process, and this charge generates an electric field that can attract or repel other objects, depending on the charges involved. The electric field is what allows charged particles to exert forces on one another, even at a distance. This is why electric forces can act over significant distances, far greater than the actual size of the particles themselves. Another aspect of charge and its relationship to the electromagnetic force is the concept of the electromagnetic wave. Electromagnetic waves, which include light, radio waves, and X-rays, are oscillating electric and magnetic fields that travel through space at the speed of light. These waves are generated when charged particles accelerate, causing ripples in the electromagnetic field that propagate outward. The most familiar form of electromagnetic waves is visible light, the type of radiation we can see with our eyes. But electromagnetic waves are not limited to visible light. They encompass a broad range of wavelengths, from the long wavelengths of radio waves to the short wavelengths of gamma rays. These waves carry energy across space, transferring information, heat, and light, and allowing for a vast array of phenomena that we observe in the world. The electromagnetic force is also responsible for the creation and manipulation of electric currents. When electrons move through a conductor such as a wire, they create an electric current, which is essentially the flow of charge. This movement of electrons is driven by an electric field, which is generated by a potential difference, or voltage, between 2 points in the conductor. The movement of these charged particles in response to an electric field is what allows us to power our devices, run our machinery, and generate all the electrical energy we rely on. Electromagnetic fields are not only responsible for the behavior of charges, but also play a critical role in the development of technologies such as motors, generators, and transformers. By manipulating the behavior of charged particles and their associated fields, we can convert mechanical energy into electrical energy and vice versa. This is the principle behind the operation of electric motors, which use magnetic fields to produce motion, and generators, which use motion to generate electricity. In this way, charge and the electromagnetic force are at the heart of modern technology, driving everything from the smallest electronic devices to the largest power plants. While charge and the electromagnetic force govern many aspects of the physical world, their reach extends far beyond everyday technology. The electromagnetic force also plays a crucial role in the behavior of light, which is a form of electromagnetic radiation. Light is not just a tool for seeing, it carries energy that can be harnessed, transmitted, and manipulated. Whether it's the light that allows us to see the world around us, or the lasers used in cutting-edge medical treatments, the interactions between charge and the electromagnetic field are fundamental to the properties and applications of light. This connection between charge and light has led to the development of fields such as optics and quantum electrodynamics, which explore the intricate behavior of light and its interactions with matter. In the grand scheme of the universe, charge and the electromagnetic force are essential components of the fabric of reality. From the formation of atoms to the generation of light, from the operation of electrical devices to the movement of galaxies, charge and its associated force shape everything in the cosmos. The electromagnetic force governs the behavior of all charged particles, whether they are tiny electrons or massive stars, and it is responsible for a vast range of phenomena, from the mundane to the extraordinary. So, what is charge? In many ways, it is the force that holds the universe together. From the smallest interactions between subatomic particles to the largest structures in the universe, charge is the unseen force that governs everything. Whether it's the attraction between electrons and protons, the flow of electricity through a circuit, or the behavior of light, charge is the cornerstone of all electromagnetic interactions. Understanding charge and the force it gives rise to is essential for understanding the very nature of the universe. And as we continue to explore these concepts, we'll uncover even more of the hidden mechanisms that govern the world around us. Charge, as we have explored, is an inherent property of particles, one that dictates how particles interact with each other through the electromagnetic force. What makes charge particularly interesting is its dual nature. There are two kinds of charge, positive and negative. These two types of charge don't just exist in isolation though, they interact in profound ways that shape the structure of matter and the universe itself. The concept of attraction and repulsion between charges is one of the most fundamental principles in physics, and it's these interactions that drive much of the behavior of the physical world. Let's start with the basics. Positive charge is carried by protons, while negative charge is carried by electrons. In this simple model, it might seem that the interaction between charges would be straightforward. If you have a positively charged particle, you would expect it to attract a negatively charged particle and repel another positively charged one. And if you have a negatively charged particle, it would attract a positively charged particle and repel another negatively charged one. These interactions, governed by the electromagnetic force, are central to the formation of atoms, the movement of electric current, and the interactions between all charged objects. At the most basic level, the interaction between positive and negative charges follows a simple principle. Opposite charges attract, and like charges repel. This means that a particle with a positive charge will pull particles with a negative charge toward it, while pushing away other positively charged particles. Similarly, a negatively charged particle will be attracted to a positively charged particle and will repel other negatively charged particles. This behaviour is what makes the world of charge so intriguing. It's governed by this simple rule. Yet the effects of this rule can be seen in complex systems ranging from the tiny scale of atoms to the vastness of cosmic structures. The force that governs these interactions is called the electrostatic force. It's the force exerted between stationary charged particles. The strength of the electrostatic force depends on the amount of charge each particle carries and the distance between them. This force can either be attractive or repulsive, depending on whether the charges are opposite or the same. When two particles with opposite charges are near each other, they will attract one another. Conversely, when two particles with the same charge are close, they will repel each other. This repulsion or attraction is the result of the electric fields generated by the charges. An electric field is essentially a region of space around a charged particle, where other charged particles feel a force. The direction of the force depends on the type of charge involved. A positively charged particle creates an electric field that points outward, while a negatively charged particle creates an electric field that points inward. This is why oppositely charged particles are drawn together, because the electric field lines point toward each other. On the other hand, like charges create fields that push away from each other, explaining the repulsion between particles with the same charge. This attraction and repulsion between charges is not just a theoretical concept, it's something that we see in action every day. Take, for example, the behaviour of static electricity. If you've ever rubbed a balloon on your hair and then stuck it to a wall, you've witnessed charge in action. The balloon becomes charged by rubbing it against your hair, and this creates a surplus of electrons on the surface of the balloon. The wall, on the other hand, becomes charged in response to the presence of the balloon. If the wall has a negative charge, it will attract the positively charged particles in the balloon, causing the balloon to stick to the wall. The attraction between the charges is so strong that the balloon stays in place despite the fact that it's not physically attached to the wall. This is a simple demonstration of the power of electrostatic attraction. Similarly, if you were to bring two balloons that have been charged in the same way, you would observe them repel each other. The reason for this is that both balloons carry a negative charge, and since like charges repel, the balloons push away from each other. This simple principle of attraction and repulsion explains not only the behaviour of balloons, but also the way in which atoms bond together to form molecules, the way electric currents flow through circuits, and the way magnets interact with each other. The interactions between positive and negative charges also have profound implications for the structure of matter. In an atom, the positively charged protons in the nucleus are balanced by the negatively charged electrons that orbit the nucleus. This balance of charges is what keeps atoms stable. If the number of protons and electrons were to change, the atom would no longer be electrically neutral and would become either positively or negatively charged. The balance between protons and electrons in atoms also plays a role in chemical reactions, as atoms can lose or gain electrons to form ions. Ions are charged particles that can interact with other ions or molecules, leading to the formation of new substances. These interactions between charged particles are the basis for chemistry, biology, and much of the world around us. The concept of attraction and repulsion between charges also extends to the macroscopic world. Electric fields created by charged particles influence not only the behaviour of other particles, but also the behaviour of objects on a larger scale. For example, electric fields are responsible for the way in which electric charges are distributed on the surface of conductors, and they govern the movement of charges in electric circuits. The design of everything from electrical wiring to circuit boards relies on an understanding of how charges interact with each other and with electric fields. This interplay between attraction and repulsion is also at the heart of the electromagnetic force. The electromagnetic force is responsible for the interactions between charged particles, but it also underlies the behaviour of light. Light itself is an electromagnetic wave, meaning it is composed of oscillating electric and magnetic fields. These fields interact with charged particles, allowing us to see and interact with the world around us. The attraction and repulsion between charges not only dictates the movement of electrons and the formation of atoms, but also governs the behavior of light, from the colours we see to the way in which light travels through space. The concept of charge and the way in which it gives rise to attractive and repulsive forces is not just confined to the microscopic scale. On the cosmic scale, the principles of charge and the electromagnetic force also play a role in the structure of the universe. Electromagnetic fields are responsible for the interaction of charged particles in space, and these fields influence the behavior of stars, galaxies, and other cosmic objects. For instance, the Sun's powerful electromagnetic fields affect the behavior of charged particles in the solar wind, which in turn influences the Earth's magnetosphere and the auroras we see in the sky. The duality of charge, positive and negative, shapes not just the behavior of matter on Earth, but also the very fabric of the universe itself. Without the attraction between positive and negative charges, atoms would not form, chemical reactions would not take place, and the electromagnetic force that governs everything from light to electricity would not exist. The interplay between attraction and repulsion is a fundamental aspect of the universe, one that governs the behavior of particles, atoms, and even galaxies. Understanding the nature of charge and the forces it gives rise to is essential for understanding the workings of the universe on every scale. To understand charge and the forces that govern its behavior, one of the most important laws we must delve into is Coulomb's law. This fundamental principle describes the force between two charged particles, giving us a mathematical framework to quantify the attractive or repulsive force that charges exert on each other. While charge itself is a property of matter, Coulomb's law allows us to measure how that property affects the behavior of charged particles in space, from atoms to larger objects. In its simplest form, Coulomb's law tells us how the electric force between two-point charges depends on two key factors: the magnitude of the charges and the distance between them. It's a relationship that is both straightforward and powerful, because it allows us to calculate the forces that govern everything, from the behavior of atoms to the forces between massive objects in space. Let's begin by breaking down Coulomb's law in more detail. The law states that the magnitude of the electric force between two-point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. In other words, if you have two charges, the force between them becomes stronger as the charges increase, and it becomes weaker as the distance between them grows. Mathematically, Coulomb's law can be written as follows: the force F between two charges is equal to a constant, known as Coulomb's constant, K, multiplied by the product of the two charges, Q1 and Q2, and divided by the square of the distance, r, between them. The equation looks something like this: F equals K times Q1 times Q2 over r squared. Here's what this equation tells us. F is the force between the two charges. K is Coulomb's constant, which has a value of approximately 8.99 times 10 to the power of 9 Newton meters squared per Coulomb squared. Q1 and Q2 represent the magnitudes of the two charges. R is the distance between the two charges. Now, this equation might seem a bit abstract, but it is incredibly useful because it gives us a way to calculate how strongly two charges interact based on their size and separation. The law applies whether the charges are positive or negative, but it's important to note that Coulomb's law takes into account both the magnitude and the sign of the charges. Like charges, whether both are positive or both negative, will result in a repulsive force, while opposite charges will result in an attractive force. The direction of the force depends on whether the charges are the same or opposite. The beauty of Coulomb's law lies in its simplicity. The force increases with the magnitude of the charges, meaning that larger charges create stronger interactions. At the same time, the force decreases with the square of the distance, which means that as charges get farther apart, the force between them becomes much weaker. This inverse square relationship is the same kind of relationship we see in gravity. where the gravitational force between two objects also decreases with the square of the distance between them. This principle has profound implications for the behavior of particles and objects in the universe. On a microscopic level, Coulomb's law explains the attraction between electrons and protons in atoms. These opposite charges are drawn together by a force that is governed by Coulomb's law, creating the stability of atoms and the foundation for chemical reactions. Without this force, atoms wouldn't hold together, and the entire structure of matter as we know it would collapse. In fact, Coulomb's law is at the heart of much of what we understand about chemistry, as the interactions between charged particles in atoms and molecules determine how they form and react with one another. But Coulomb's law doesn't just apply to atoms, it also governs the behavior of charged objects on much larger scales. For example, consider two electrically charged spheres. According to Coulomb's law, if you know the magnitude of the charges and the distance between them, you can calculate the force that will either attract or repel them. This principle is used in everything from designing electrical circuits to understanding the behavior of charged particles in space. It also helps explain how lightning works, as the build-up of electrical charges in clouds leads to an intense discharge of energy between the clouds and the ground. One important thing to note about Coulomb's law is that it assumes the charges in question are point charges, which means that they are treated as though they are concentrated at a single point in space. This is an idealized situation that works well for small, isolated charges. However, for more complex systems, such as extended bodies with distributed charge, or for charges within atoms and molecules, the situation becomes more complicated. Even so, Coulomb's law remains an invaluable tool for understanding and predicting the behavior of charges, both in the microscopic world of particles and in the macroscopic world of objects. Coulomb's law is also crucial for understanding the concept of electric fields. As we discussed earlier, an electric field is a region of space around a charged particle, where other charged particles feel a force. The electric field is directly related to the force described by Coulomb's law. In fact, Coulomb's law is the foundation of the concept of the electric field, as it tells us how the strength of the electric field at a particular point in space depends on the magnitude of the charge and the distance from the charge. The electric field is simply a way of describing how a charge interacts with the space around it, without needing to consider the direct force between charges. In a similar way, Coulomb's law helps explain how charged objects interact with each other through the electromagnetic force. The law tells us that the force between charges is a function of both their magnitudes and the distance between them, and this force is what governs the behavior of charges in electric circuits, electrical fields, and many other phenomena. Understanding Coulomb's law, therefore, is a fundamental part of understanding how electricity and magnetism work in the world around us. But Coulomb's law is not just about understanding the forces between particles. It also leads us into a deeper exploration of the nature of force itself. The inverse square relationship between the distance and the force is a key feature of many forces in nature, and it reveals something profound about the geometry of space. Forces that decrease with the square of the distance, such as gravity and the electromagnetic force, are a sign of the underlying symmetry of space. The fact that both the electric and gravitational forces follow this pattern tells us that these forces are tied to the very structure of the universe itself, shaping everything from the smallest subatomic particles to the largest galaxies. It's also important to note that Coulomb's law doesn't just apply to everyday situations. In fact, this law has been critical in our understanding of particle physics, astrophysics, and many other fields. From the behavior of atoms to the formation of stars, Coulomb's law provides a way of calculating and predicting the forces that govern the interactions of charged particles in the universe. Whether we're looking at the forces inside a hydrogen atom or the behavior of plasma in the vast reaches of space, Coulomb's law remains a cornerstone of physics. One of the most intriguing aspects of Coulomb's law is its role in the development of electromagnetic theory. As we look deeper into the nature of electric and magnetic fields, we begin to see how Coulomb's law interacts with other fundamental principles, such as Ampere's law and Faraday's law of induction. These laws combine to give us a complete picture of electromagnetism, which is essential for understanding the behaviour of everything from light to radio waves to the workings of the devices that power our modern world. As we continue to explore the nature of charge and its interactions, Coulomb's law will remain a fundamental tool for understanding the forces at play. Whether we're calculating the force between particles in an atom, or predicting the behaviour of charged objects in an electric field, this law provides a solid foundation for our understanding of the electromagnetic force. But even more importantly, Coulomb's law opens the door to deeper questions about the nature of forces and the structure of the universe. It's a law that connects the behaviour of individual particles to the vast and complex interactions that govern the cosmos, and it's one that will continue to play a key role in our ongoing exploration of the physical world. Charge is a concept that, while fundamental, takes on a different character when we enter the world of quantum mechanics. At the macroscopic level, charge behaves in ways we can intuitively grasp. Positive and negative charges attract or repel each other based on the laws of electrostatics. However, when we zoom in on the subatomic scale, the behaviour of charge becomes far less intuitive, governed by the principles of quantum mechanics. The quantum nature of charge opens up a world where particles don't just follow classical trajectories, but instead exist in probabilistic states and interact in strange and unexpected ways. This chapter will explore what charge is at the quantum level and how its behaviour changes when we take the leap from the classical to the quantum world. In classical physics, we think of charge as something that is attached to a particle, a tangible and measurable property that can be quantified and understood through force fields and interactions. But in quantum mechanics, things are not so simple. Particles like electrons, which carry negative charge, do not have definite positions or trajectories in the way that classical objects do. Instead, their locations are described by wave functions, mathematical functions that give the probability of finding a particle in a particular location at any given time. This is known as the principle of superposition, where particles exist in a combination of states rather than a single definite state. The quantum nature of charge becomes particularly evident when we think about the behaviour of electrons in atoms. In a classical model of the atom, electrons would orbit the nucleus in well-defined paths, similar to planets orbiting the Sun. But in reality, electrons don't follow such neat, predictable orbits. Instead, their position is described by a probability distribution, an area around the nucleus where the electron is most likely to be found. This is known as the electron cloud. The idea of the electron being in a specific place at any given time is replaced by a description of where it might be found, based on the probability that the electron will appear in a given region. This probabilistic behaviour is a direct result of the principles of quantum mechanics. In the quantum world, particles like electrons don't have fixed properties until we measure them. Instead, their properties, such as position, momentum, and charge, exist in a state of probability, spread out over a range of possibilities. When we perform an experiment to measure a property of a particle, such as its position, we collapse the wave function, forcing the particle to take on a definite value. Until we make that measurement, however, the particle exists in a superposition of states. One of the key principles of quantum mechanics that influences the behaviour of charge is the concept of quantization. Charge, like energy and other physical properties, is quantized in the quantum world. This means that charge doesn't exist in just any amount, but rather in discrete packets, or quanta. For example, the charge of an electron is a specific fixed amount, approximately minus 1.6 times 10 to the power of minus 19 coulombs. In other words, the charge of an electron is an indivisible unit. It cannot be divided into smaller amounts. This quantization of charge is a feature of the quantum world and helps explain the discrete nature of atomic and subatomic phenomena. In addition to the quantization of charge, Another crucial aspect of the quantum nature of charge is the concept of charge interactions in quantum field theory. Quantum field theory, QFT, is the framework that combines quantum mechanics with special relativity to describe the behavior of particles and fields. In QFT, particles like electrons are not treated as individual points in space, but rather as excitations in an underlying quantum field. This field is spread out through all of space, and particles are simply localized regions of the field that we perceive as individual particles. The electromagnetic field, for example, is a quantum field that governs the interactions between charged particles. In QFT, the exchange of particles, such as photons, carries the electromagnetic force between charged particles. When two electrons, for example, interact with each other, they exchange photons, particles of light, creating the electromagnetic force between them. This exchange of photons is what allows the electric and magnetic forces to act at a distance, despite the fact that the particles themselves are not directly touching. The concept of particles interacting through the exchange of other particles is known as particle exchange, and it's a fundamental part of quantum field theory. The interaction of charge with electromagnetic fields at the quantum level also leads to some surprising and counterintuitive results. For example, the electromagnetic force between charged particles can be mediated by virtual photons, particles that exist for incredibly short times and cannot be directly observed. These virtual photons are exchanged between particles in a way that allows them to influence each other without physically touching. This concept of virtual particles, while strange, is essential to understanding the nature of force at the quantum level. The quantum nature of charge also gives rise to phenomena that are purely quantum in nature. One such phenomenon is the concept of charge quantization in atoms. In a classical atom, electrons could occupy any energy level, but in a quantum atom the energy levels are quantized, meaning that electrons can only exist in specific energy states. This is because the electron's charge in the quantum world can only exist in discrete amounts. As a result, the electron must occupy specific orbits around the nucleus, and when it moves between these orbits, it must absorb or emit specific amounts of energy. This process of energy quantization explains many of the spectral lines we observe in atoms, such as the characteristic colours emitted by hydrogen when it is excited by energy. The electron transitions between quantized energy levels, emitting photons of specific energies that correspond to those spectral lines. Another important quantum effect related to charge is the phenomenon of electric charge in quantum systems that exhibit wave-particle duality. Wave-particle duality is the idea that particles like electrons can exhibit both particle-like and wave-like behaviour, depending on how they are observed. In the case of charge, this means that electrons can exhibit interference patterns just like waves do. When electrons are fired through a double-slit apparatus, for instance, they behave like waves, creating an interference pattern on a screen. However, when we observe the individual electrons, they behave like particles, landing in specific locations. This wave-particle duality is a central feature of quantum mechanics and is deeply tied to the behaviour of charge. One of the most profound implications of the quantum nature of charge is its role in the uncertainty principle. The uncertainty principle, proposed by Werner Heisenberg, states that it is impossible to simultaneously know both the position and momentum of a particle with absolute certainty. This principle is a fundamental feature of quantum mechanics and applies to all particles, including those that carry charge. Because we cannot precisely measure both the position and momentum of an electron, we cannot precisely determine its trajectory. This uncertainty has far-reaching implications for our understanding of the behaviour of charged particles and the interactions between them. It's one of the reasons why quantum systems, including the behaviour of electrons in atoms, are inherently unpredictable and probabilistic. The quantum nature of charge is also evident in more complex systems, such as superconductivity and the behaviour of charge in condensed matter physics. In superconductors, for example, charge flows without resistance, a phenomenon that can only be understood through quantum mechanics. The quantum behavior of charge in these systems leads to new technologies, including quantum computers, which rely on the manipulation of charged particles in quantum states. In summary, charge in the quantum world is far more than just a simple property that particles carry. It is a key player in the probabilistic and quantized nature of the subatomic world. The quantum behavior of charge leads to effects like wave-particle duality, energy quantization, and the exchange of virtual particles, all of which contribute to the complex and fascinating interactions between charged particles. These quantum effects not only explain the behavior of atoms and molecules, but also give rise to new technologies that are revolutionizing the way we interact with the world. The quantum nature of charge is a reminder that, in the microscopic world, the rules are very different from those of classical physics, and our understanding of charge continues to evolve as we explore the strange and captivating world of quantum mechanics. Charge, as we have seen, is a fundamental property of particles that can exert powerful forces on other charged particles. But what happens when these charges are in motion? When charges move, they create something we encounter every day: electric current. Electric current is the flow of charge, typically carried by electrons in a conductor, and it plays a central role in many of the technologies that power our modern world. In this chapter, we will explore how charge in motion gives rise to electric current, the mechanisms that govern this flow, and how we can harness it to generate energy, power devices, and facilitate communication. At its core, electric current is simply the movement of charged particles. In most cases, these charged particles are electrons, which are negatively charged. However, other types of charge carriers can also contribute to electric current, depending on the material. For example, in certain types of materials like metals, electrons are the primary charge carriers, while in the electrolytes and some semiconductors, ions, positively or negatively charged atoms or molecules, can also carry charge. The movement of these charge carriers through a material is what we call electric current. In a conductor, such as a copper wire, electrons are relatively free to move. These electrons are part of the outermost regions of atoms, which are not tightly bound to their nuclei. When a potential difference or voltage is applied across the conductor, usually by a power source like a battery or a generator, an electric field is created. This electric field pushes the free electrons in the conductor, causing them to move. The flow of electrons from one place to another in response to this electric field is what we perceive as electric current. The key to understanding electric current lies in recognizing that the movement of electrons is not random. Instead, it is a directed flow caused by the electric field, which pushes electrons in a particular direction. In a sense, the electric field serves as the driving force behind the motion of charge. However, as the electrons move through the conductor, they experience resistance, which is the opposition to their flow. This resistance is due to the interactions between the electrons and the atoms in the material, which cause the electrons to lose some of their energy in the form of heat. The relationship between the electric field, the current, and the resistance in a conductor is described by Ohm's law, one of the most fundamental equations in electrical engineering and physics. Ohm's law states that the current I flowing through a conductor is directly proportional to the voltage, V, applied across the conductor and inversely proportional to the resistance, R, of the conductor. Mathematically, Ohm's law can be written as I equals V over R. This simple equation tells us that if we increase the voltage, the current will increase, assuming the resistance remains constant. Conversely, if we increase the resistance, the current will decrease for a given voltage. This relationship is central to the design of electrical circuits and the behavior of current in different materials. While Ohm's law provides a straightforward way to understand current flow, there are more subtle factors at play when charges are in motion. One of the most interesting phenomena related to moving charge is the generation of magnetic fields. When charges move through a conductor, they create a magnetic field around the wire. This is known as Ampere's law, which describes the magnetic field generated by an electric current. The direction of the magnetic field depends on the direction of the current, and this relationship is the basis for the operation of devices like electromagnets and electric motors. The magnetic field generated by an electric current is not just a theoretical concept, it has real-world applications. For example, electromagnets use electric current to create a magnetic field that can be turned on and off, making them useful in a wide range of applications from medical imaging, MRI machines, to electric motors that power everything from fans to cars. The ability to control magnetic fields through electric currents is a cornerstone of modern technology. Another important phenomenon related to the motion of charge is the flow of current in circuits. A circuit is simply a closed loop through which charge can flow. The simplest circuit consists of a power source, such as a battery, connected to a conductor, like a wire, and a load, like a light bulb. When the circuit is completed, the voltage from the power source creates an electric field that drives the flow of electrons through the conductor, causing the light bulb to light up. This is an example of how electric current can be harnessed to do useful work. In more complex circuits, multiple components are connected in series or parallel to control the flow of current and manage the distribution of voltage. For example, in a series circuit, the current flows through each component in sequence, so if one component is removed, the entire circuit is broken. In a parallel circuit, the components are connected in multiple branches, so if one branch is broken, current can still flow through the other branches. Understanding how current behaves in these different types of circuits is essential for designing electrical systems and devices. The ability to control the flow of electric current has profound implications for our daily lives. In fact, much of the modern world depends on the efficient movement of charge. From powering homes and businesses with electricity to enabling communication through the internet, electric current is at the heart of the technologies that shape our world. The development of electrical power systems, from early generators to modern power grids, has made it possible to generate and distribute electricity to millions of people. Similarly, advances in electronics, from radios to smartphones, rely on the precise manipulation of electric current to perform tasks ranging from amplifying signals to processing information. One of the most important applications of electric current is in the generation of energy. In power plants, electric current is generated by moving a conductor through a magnetic field, a process known as electromagnetic induction. This motion generates an electric current, which is then transmitted to homes and businesses for use. The movement of charge through conductors is central to this process, and it allows us to harness the power of mechanical energy, from steam, water, or wind, to generate electricity. Electric current is also critical to the operation of modern electronics. From the smallest microprocessors and computers to the largest power distribution systems, the flow of charge through circuits is essential for the functioning of electronic devices. In a microprocessor, for example, billions of transistors are used to control the flow of current, enabling the processing of information. In this way, charge in motion is directly tied to the processing and transmission of data, making it a foundational component of the information age. The study of electric current also leads us to a deeper understanding of the behavior of materials. Different materials have different properties when it comes to conducting electric current. Conductors, such as metals like copper and aluminum, allow charge to flow easily through them, while insulators, such as rubber and plastic, resist the flow of charge. Semiconductors, materials like silicon, are somewhere in between. They can conduct charge under certain conditions but resist it under others. The discovery and manipulation of these materials has paved the way for the development of everything from transistors to solar panels. As we continue to explore the nature of charge in motion, it's clear that electric current is not just a simple flow of particles. It is a dynamic phenomenon with far-reaching consequences, from the fundamental behavior of matter to the complex technologies that define our modern world. Whether we are generating electricity, powering devices, or transmitting information, electric current plays an essential role in shaping the way we live. the study of charge in motion continues to be a central focus in the fields of physics, engineering and technology, and it will undoubtedly drive further innovations in the future. In summary, electric current is the flow of charge, typically carried by electrons, through a conductor in response to an applied electric field. The movement of charge is governed by principles such as Ohm's law, which describes the relationship between voltage, current and resistance. The motion of charge also generates magnetic fields, which have wide-ranging applications in technology. Whether we are using electric current to power homes, run electronics or generate energy, it is one of the most important phenomena in the physical world. Understanding how charge moves is key to understanding how we harness and control the power of electricity, and it remains a cornerstone of modern science and technology. Charge and magnetism are inextricably linked through the electromagnetic force, one of the four fundamental forces of nature. While we often think of charge in the context of electricity, where it manifests as the flow of electrons or the interaction between charged particles, charge also plays a crucial role in the creation and behavior of magnetic fields. Understanding the relationship between charge and magnetism is essential for explaining a wide range of phenomena, from the operation of magnets to the functioning of electric motors and generators. In this chapter, we'll explore the role of charge in magnetism and how these two forces interact to shape the world around us. The first step in understanding the connection between charge and magnetism is recognizing that moving charge creates a magnetic field. This is a fundamental principle that underpins much of electromagnetism. When charged particles, such as electrons, are in motion, they generate a magnetic field that extends around them. This magnetic field is not confined to the particle itself, but radiates outward into the surrounding space. The faster the charge moves, the stronger the magnetic field it generates. This phenomenon is described by Ampere's law, which states that an electric current, which is essentially a flow of charge, produces a magnetic field around it. This principle is the foundation of many technological applications, from electromagnets to the operation of electric motors. One of the simplest and most common examples of charge's role in magnetism is the magnetic field produced by a current-carrying wire. When an electric current flows through a conductor, such as a copper wire, it generates a magnetic field around the wire. This magnetic field forms concentric circles around the wire, with the direction of the field depending on the direction of the current. If you were to wrap the wire into a loop or coil, the magnetic field produced by the current would become more concentrated, creating a stronger magnetic field. This is the principle behind the creation of electromagnets, which are used in countless applications, from MRI machines to electric motors. But the connection between charge and magnetism goes beyond just the creation of magnetic fields by current. It also explains how magnets themselves work. Magnets, whether they are permanent magnets or electromagnets, are essentially materials that have charges in motion within them. In a permanent magnet, such as a bar magnet, the electrons within the material are arranged in such a way that their individual magnetic moments add up to create an overall magnetic field. This is a result of the motion of electrons within the atoms of the material. In simple terms, each electron generates a tiny magnetic field as it orbits the nucleus of an atom, and in a magnet these individual magnetic moments align to produce a collective magnetic field. The strength and orientation of the magnetic field produced by a magnet depend on how the charges within the material are arranged. In most materials, the magnetic moments of the electrons are randomly oriented, so they cancel each other out, and the material does not behave as a magnet. However, in ferromagnetic materials like iron, the magnetic moments of the electrons tend to align in the same direction, resulting in a net magnetic field. This alignment is what makes permanent magnets so powerful and allows them to attract or repel other magnetic materials. It's important to note that the connection between charge and magnetism is not just limited to moving charge in conductors or within materials like magnets. The fundamental relationship between electricity and magnetism also plays a key role in the propagation of electromagnetic waves, such as light. In fact, light is an electromagnetic wave composed of oscillating electric and magnetic fields that travel through space at the speed of light. These waves are created by the acceleration of charged particles, and their behavior is governed by the interplay between electric and magnetic fields. This relationship between charge, electricity, and magnetism is encapsulated in the famous set of equations known as Maxwell's equations, which form the foundation of classical electromagnetism. Maxwell's equations describe how electric and magnetic fields interact with each other and with charged particles. They show that a changing electric field generates a magnetic field, and vice versa. This means that when charges are accelerated, they not only generate electric fields, but also produce magnetic fields. In the case of an alternating current, AC, for example, the direction of the current changes periodically, causing the magnetic field to oscillate as well. This oscillating electric and magnetic field propagates outward in the form of an electromagnetic wave. This is how radio waves, light, and other forms of electromagnetic radiation travel through space. The interaction between charge and magnetism is also central to the operation of electric motors and generators, devices that convert electrical energy into mechanical energy and vice versa. In an electric motor, an electric current is passed through a coil of wire placed within a magnetic field. The interaction between the magnetic field and the current creates a force that causes the coil to rotate. This is an example of the Lorentz force, which is the force exerted on a charged particle moving through a magnetic field. The direction of the force depends on the direction of the current and the magnetic field, and this interaction is what allows motors to produce motion. In a generator, the process is reversed. Mechanical motion is used to move a coil of wire through a magnetic field, generating an electric current. The relationship between charge and magnetism is not limited to the devices we use in our everyday lives. It also plays a crucial role in understanding the behavior of charged particles in space. For example, the Earth's magnetic field generated by the motion of molten iron in the planet's core helps protect the planet from the harmful effects of solar radiation. The charged particles in the solar wind, which are predominantly electrons and protons, interact with the Earth's magnetic field, causing the formation of the auroras near the poles. These stunning light displays are a result of charged particles being funneled into the Earth's atmosphere, where they interact with atoms and release energy in the form of light. Magnetism is also key to understanding the behavior of cosmic objects like stars and galaxies. The Sun's magnetic field plays a crucial role in the dynamics of solar activity, such as sunspots, solar flares, and coronal mass ejections. These phenomena are caused by the interaction of the Sun's magnetic field with the charged particles in the solar wind. Similarly, the magnetic fields of planets, moons, and other celestial bodies affect the behavior of charged particles in space, influencing everything from planetary atmospheres to cosmic radiation. In addition to these macroscopic phenomena, the role of charge in magnetism is also important in understanding the behavior of charged particles in accelerators and other high-energy experiments. In particle accelerators, charged particles are propelled to high speeds using electric fields, and their interactions with magnetic fields are used to control their paths. These experiments allow scientists to probe the fundamental nature of matter and the forces that govern the universe, providing insights into everything from the structure of atomic nuclei to the origins of the universe itself. The relationship between charge and magnetism is central to our understanding of the physical world. From the behavior of electrons in atoms to the dynamics of celestial bodies, from the operation of motors to the generation of electromagnetic waves, the interaction between charge and magnetic fields shapes much of the universe. It's a force that governs the motion of particles, the behavior of light, and the functioning of many of the technologies that define modern life. The study of this connection continues to drive advances in physics, engineering, and technology, and it remains one of the most important areas of research in the sciences. In summary, charge plays a crucial role in the generation of magnetic fields and the behaviour of magnetism. Moving charge creates magnetic fields, and these fields interact with other charges to produce forces that shape the behaviour of matter and energy. The relationship between charge and magnetism is at the heart of electromagnetism, a fundamental force that governs everything from the behaviour of atoms to the motion of celestial bodies. Understanding this connection is essential for explaining many of the phenomena we encounter in our everyday lives, and for developing new technologies that harness the power of electricity and magnetism. The concept of charge conservation is one of the most fundamental principles in physics. It states that the total electric charge in an isolated system remains constant over time. In other words, charge cannot be created or destroyed, only transferred or redistributed. This principle, known as the law of conservation of charge, is a cornerstone of our understanding of the behaviour of charge and the interactions between charged particles. It helps to explain everything from the behaviour of electrical circuits to the fundamental nature of physical processes in the universe. To understand charge conservation, we first need to appreciate the fact that charge is a quantized property. The smallest possible amount of charge is the charge of an electron, which is approximately minus 1.6 times 10 to the power of minus 19 coulombs. This is the fundamental unit of negative charge. The same amount of positive charge is carried by the proton. Importantly, charge always exists in integer multiples of this elementary charge. This means that there is no fractional charge. Charge is always an integer multiple of the charge of an electron or proton. In an isolated system, such as a closed circuit or a collection of particles, the total amount of charge remains unchanged. This means that if you have a system with a certain amount of charge at the beginning of an interaction, you can predict that the same amount of charge will exist at the end of that interaction. This is true even if the individual particles in the system exchange or redistribute charge. The total charge, however, will stay the same. This principle is exemplified in many everyday situations. For example, consider the case of a charged balloon. If you rub a balloon on your hair, electrons are transferred from your hair to the balloon, giving the balloon a negative charge. However, the total charge in the system, including both the balloon and your hair, remains the same. If the balloon acquires a negative charge, your hair must acquire a positive charge to balance it out. The total charge before and after the rubbing process is conserved. Even though the charges are redistributed, no charge is lost or created in the process. The law of conservation of charge also applies to more complex systems, including electrical circuits and particle interactions. In a circuit, the movement of charge through conductors may cause electrons to flow through wires, light bulbs, or other components. While electrons may leave one part of the circuit and enter another, the total charge in the circuit remains the same. If charge were not conserved, you would expect to see a build-up of charge in one part of the circuit, or a net loss of charge in the system, which would violate the conservation principle. One important application of charge conservation is in the field of particle physics, where particle collisions and interactions often involve the exchange of charge between particles. In these interactions, the total charge before and after the collision remains constant. For example, when an electron and a positron, the antimatter counterpart of the electron, collide, they annihilate each other, producing photons. However, the total charge before and after the interaction is zero, because the electron and positron have equal and opposite charges, and the photons produced carry no charge. In this case, charge is conserved, even though the particles themselves are destroyed in the interaction. The conservation of charge is also closely related to the concept of symmetry in physics. Symmetry in this context refers to the idea that certain properties of a system remain unchanged under specific transformations. In the case of charge conservation, the symmetry is the invariance of the total charge in a system. This symmetry is a reflection of the underlying laws of nature, which dictate that charge is always conserved. This concept is not only important in classical physics, but also plays a crucial role in modern theories of particle physics, including the Standard Model. In quantum mechanics, the law of conservation of charge is even more fundamental. In particle interactions at the quantum level, such as those described by quantum electrodynamics, QED, charge conservation is strictly upheld. For instance, in the process of particle-antiparticle creation or annihilation, the total charge is always conserved. The conservation of charge is a direct consequence of the fundamental symmetry of the laws of nature, and it is one of the most important constraints on physical processes. The conservation of charge is also critical in understanding the behavior of electric fields and the interactions between charged particles. When two charged objects interact, they exchange electric fields, which cause the particles to exert forces on each other. While the distribution of charge may change during the interaction, the total charge in the system remains constant. This is true even in the most complex situations, such as when charges move through a conductor or when particles interact at high energies. One of the most important consequences of the law of conservation of charge is that it allows us to predict the behavior of systems involving charge. Whether we are analyzing the flow of current in a circuit, studying the interactions between charged particles in a plasma, or investigating the behavior of particles in high-energy experiments, the conservation of charge is a key principle that helps us make accurate predictions about how charge will behave. It's also worth noting that the conservation of charge is closely related to other fundamental conservation laws in physics, such as the conservation of energy and momentum. These laws are all linked through the symmetries of the universe, which dictate that certain quantities remain constant over time. In the case of charge, this symmetry leads to the law of charge conservation, which tells us that the total charge in a closed system is constant, no matter how charge is redistributed or transferred within that system. In some cases, charge conservation is also tied to the concept of gauge symmetry, which is a cornerstone of modern physics. Gauge symmetry refers to the idea that certain physical quantities, such as charge, are related to the symmetries of the laws governing particles and forces. In the context of electromagnetism, the gauge symmetry is associated with the conservation of electric charge, as well as the invariance of the electromagnetic field under certain transformations. This concept is a central part of the Standard Model of particle physics, which describes the fundamental forces and particles of the universe. While the law of conservation of charge is a fundamental principle, it is not just a theoretical idea. It has practical implications that influence many aspects of our daily lives. From the operation of electrical devices to the functioning of the global power grid, the conservation of charge plays a vital role in the design and functioning of modern technologies. Understanding how charge is conserved in electrical circuits, for example, is crucial for engineers designing efficient power systems and for scientists developing new technologies that rely on the movement of charge, such as quantum computers and nanotechnology. One of the more fascinating areas of research related to charge conservation involves the study of neutrinos. Neutrinos are subatomic particles that are electrically neutral and interact very weakly with matter. While neutrinos do not carry charge, they play an important role in particle interactions where charge is transferred between other particles. For example, in beta decay, a neutron decays into a proton, an electron, and an antineutrino. The total charge before and after the decay remains the same, as the neutron is neutral and the proton is positively charged. This process is an example of charge conservation at work in particle physics. In summary, the law of conservation of charge is a fundamental principle that governs the behavior of electric charge in the universe. It states that the total charge in an isolated system remains constant, regardless of the interactions or redistributions of charge that may occur. This principle underlies much of the behavior of charged particles, from the operation of electrical circuits to the interactions between particles in high-energy physics. Charge conservation is a direct consequence of the symmetries of the laws of nature, and it plays a crucial role in making predictions about the behavior of charge in various systems. Whether we are studying the flow of electrons through a wire or investigating particle interactions in a collider, the law of charge conservation is always at work, shaping the way charge behaves in the physical world. Electromagnetic fields are among the most important and pervasive phenomena in the universe. Though we cannot see them directly with our eyes, their effects are all around us, shaping the behavior of charged particles, guiding the flow of electricity, and even influencing light. These invisible fields are responsible for the vast majority of interactions in the microscopic world, from the structure of atoms to the dynamics of chemical reactions. At the macroscopic level, electromagnetic fields control the behavior of all things electric, from the current in your phone charger to the operation of large power grids. But to fully appreciate their significance, we need to explore what electromagnetic fields are, how they arise, and how they govern the interactions between charges. At their core, electromagnetic fields are the result of interactions between charged particles. When a charged particle moves, it creates an electric field around it. This electric field exerts a force on other charged particles in the vicinity. In turn, the motion of charged particles can also generate a magnetic field. These two fields, electric fields and magnetic fields, are intimately connected, and together they form the electromagnetic field. The electric field is created by stationary charges, and it is responsible for the electrostatic forces that act between charges. If you place a positive charge in space, it creates an electric field that extends outward from the charge, and other charges within this field will feel a force. For example, a negative charge will be attracted to the positive charge because the electric field exerts an attractive force between them. The strength of the electric field at a given point depends on the amount of charge creating the field and the distance from the charge. The greater the charge, the stronger the electric field, and the closer you are to the charge, the stronger the field will be. Magnetic fields, on the other hand, are generated by moving charges. When an electric current flows through a wire, for example, it creates a magnetic field that surrounds the wire. This is the basis for electromagnets, which use electric current to generate magnetic fields that can be turned on and off. The magnetic field produced by moving charges is not just a theoretical concept. It has real, measurable effects. For example, if you place a compass near a current-carrying wire, the needle will align with the magnetic field generated by the current. This is one of the ways we can directly observe the influence of magnetic fields. The electric and magnetic fields are not independent of each other. They are part of a single, unified entity, the electromagnetic field. This interconnection was first described by James Clerk Maxwell, whose equations form the foundation of classical electromagnetism. Maxwell's equations show that a changing electric field generates a magnetic field, and vice versa. This relationship means that electric and magnetic fields are intimately tied together in a way that allows them to propagate through space as electromagnetic waves. Electromagnetic waves, such as light, radio waves, and X-rays, are disturbances in the electromagnetic field that travel through space. These waves consist of oscillating electric and magnetic fields that move perpendicular to each other and to the direction of the wave's propagation. For example, in the case of visible light, the electric field oscillates in one direction, while the magnetic field oscillates in a direction perpendicular to the electric field. These oscillating fields travel outward from their source at the speed of light, carrying energy across vast distances. The study of electromagnetic waves is central to understanding everything from wireless communication to the behavior of light and radiation. Maxwell's theory revolutionized our understanding of electromagnetism by unifying electricity and magnetism into a single theory. Before Maxwell, electric fields and magnetic fields were thought of as separate phenomena, each governed by its own set of laws. But Maxwell showed that they are part of the same underlying reality. The behavior of electric fields can generate magnetic fields, and the behavior of magnetic fields can generate electric fields. This duality is at the heart of the electromagnetic field. One of the most important aspects of electromagnetic fields is that they exert forces on charged particles. This is the force that drives the movement of electrons in electric circuits and determines the behavior of charged particles in a wide range of physical processes. The electromagnetic force is responsible for the interaction between particles in atoms and molecules, dictating the formation of bonds and chemical reactions. It's also the force that governs the propagation of light, from the glow of a light bulb to the transmission of radio waves. In addition to the forces between charged particles, electromagnetic fields are also responsible for phenomena such as the reflection and refraction of light. When light travels from one medium to another, such as from air to water, the electromagnetic field interacts with the atoms in the materials, causing the light to bend. This is why a straw in a glass of water appears to be broken at the water's surface. The electromagnetic interaction between the light and the water's atoms causes the light to change direction, a phenomenon known as refraction. Electromagnetic fields also play a critical role in modern technology. For example, in electric motors, a magnetic field interacts with a current-carrying conductor to produce motion. In generators, the reverse process occurs. Motion is used to create an electric current. These devices rely on the interaction between electric and magnetic fields to convert energy from one form to another. The principles of electromagnetism are also behind technologies like transformers, which allow us to transmit electrical power efficiently over long distances, and wireless communication, which uses electromagnetic waves to transmit data across space. The role of electromagnetic fields extends beyond Earth-bound applications, influencing the behavior of objects in space. The Earth's magnetic field, for example, protects us from the harmful effects of solar radiation. The charged particles in the solar wind are deflected by the Earth's magnetic field, preventing them from reaching the surface and causing damage to our atmosphere. The auroras, or northern and southern lights, are a visible manifestation of the interaction between the solar wind and the Earth's magnetic field. When charged particles from the solar wind collide with the atoms in the Earth's atmosphere, they release energy in the form of light, creating these beautiful displays. In addition to the Earth's magnetic field, the magnetic fields of other celestial bodies such as the Sun influence the dynamics of space weather and the behavior of charged particles in space. Solar storms, for instance, are the result of intense activity on the Sun's surface that releases large amounts of charged particles into space. These particles interact with the Earth's magnetic field, leading to disturbances in satellite communications, power grids, and navigation systems. Electromagnetic fields also govern the behavior of plasma, the fourth state of matter. Plasma consists of ionized gas, where electrons are separated from their atomic nuclei, creating a soup of charged particles. The behavior of plasma is governed by electromagnetic forces, and plasma plays a central role in everything from the solar wind to the functioning of fusion reactors. In plasma physics, understanding the behavior of electromagnetic fields is crucial for controlling and manipulating plasmas for various applications, including energy generation and space propulsion. The study of electromagnetic fields has led to numerous technological advancements and scientific discoveries. From the development of electric power generation and distribution to the invention of the radio, the understanding of electromagnetic fields has shaped the modern world in profound ways. It has also opened up new areas of exploration, such as the study of the interaction between electromagnetic fields and matter, the development of quantum electrodynamics, and the search for new forms of energy. In summary, electromagnetic fields are invisible forces that arise from the interaction of charged particles. These fields govern the behavior of matter on all scales, from the microscopic interactions between atoms to the large-scale dynamics of celestial bodies. The relationship between electric and magnetic fields is at the heart of many of the phenomena we observe in the universe, from the propagation of light to the functioning of electric motors. Understanding electromagnetic fields is essential for explaining a wide range of physical processes and for developing the technologies that power our modern world. Whether we are studying the forces between particles in atoms or exploring the behavior of plasma in space, electromagnetic fields are a fundamental part of the fabric of the universe. In the world of charge, one of the most important concepts to understand is that of charge carriers. These are the particles that actually move and carry electric charge through materials, allowing electric currents to flow. Whether in a wire, an electrolyte, or a plasma, charge carriers are responsible for the movement of charge that powers everything from the devices in your home to the processes that happen inside your body. But what exactly are charge carriers, and how do they work? In this chapter, we'll explore the nature of charge carriers, focusing on two of the most important types, electrons and ions. At the most basic level, a charge carrier is any particle that has an electric charge and can move within a material. The movement of these charged particles is what constitutes an electric current. In most conductive materials, like metals, the primary charge carriers are electrons. Electrons are subatomic particles that carry a negative charge and are found in the outer regions of atoms. Because electrons are much lighter than protons and neutrons, they are more easily displaced when an electric field is applied, allowing them to move freely through conductors like copper, aluminum, or silver. The behavior of electrons in a conductor is central to our understanding of electricity. In a metal, the outermost electrons of atoms are not tightly bound to their respective nuclei. These electrons form what is known as an electron sea, where they can move relatively freely within the material. When a voltage is applied across a conductor, an electric field is created, and this field exerts a force on the free electrons, causing them to drift in the direction of the field. This movement of electrons constitutes electric current. In addition to being the primary charge carriers in metals, electrons are also responsible for the flow of charge in semiconductor materials. Semiconductors, like silicon, have properties that allow them to conduct charge under certain conditions but not under others. In a semiconductor, electrons in the material can be excited into higher energy states, allowing them to move and carry charge. This controlled movement of electrons in semiconductors is the basis for many modern technologies, including computers, solar cells, and LEDs. However, electrons are not the only particles that can carry charge. In certain materials, particularly liquids and gases, ions can also serve as charge carriers. Ions are atoms or molecules that have gained or lost one or more electrons, giving them a net electric charge. An atom that has lost one or more electrons becomes a positively charged ion, while an atom that has gained electrons becomes a negatively charged ion. In liquids, particularly electrolytes, ions are the primary charge carriers. For example, in a salt solution, such as when sodium chloride, NaCl, is dissolved in water, the sodium ions, Na+, and chloride ions, Cl-, are free to move through the solution. When a voltage is applied, the positive sodium ions move toward the negative electrode, and the negative chloride ions move toward the positive electrode. This movement of ions is what constitutes an electric current in electrolytes, much like the movement of electrons in a wire. The role of ions as charge carriers is not limited to electrolytes. In biological systems, ions are crucial for the movement of charge across cell membranes. For example, the sodium-potassium pump in nerve cells uses the movement of sodium, Na+, and potassium, K+, ions, to generate electrical signals that are essential for nerve function. This movement of ions across cell membranes is a key part of how the body communicates and processes information. Ions are also important in the behavior of plasmas. Plasmas are ionized gases composed of free electrons and ions, and they are found in a variety of environments, from the sun to fluorescent lights. In a plasma, the movement of both electrons and ions carries charge and allows the plasma to conduct electricity. The behavior of ions and electrons in a plasma is governed by the electromagnetic fields present, and plasmas can exhibit fascinating phenomena such as lightning, auroras, and the behavior of plasma in fusion reactors. While electrons and ions are the most common charge carriers, they are not the only ones. For example, in some materials such as certain semiconductors, other types of particles like holes can also act as charge carriers. A hole is essentially the absence of an electron in a material. In a semiconductor, when an electron moves from one location to another, it leaves behind a hole, which behaves like a positive charge carrier. The movement of holes in a semiconductor can contribute to the flow of charge in the material, and this is an important concept in understanding the behavior of semiconductors in devices like diodes and transistors. Charge carriers are not only important for understanding the flow of charge, but also for understanding how materials conduct electricity. The ability of a material to conduct electricity depends on the availability and mobility of charge carriers. In conductors, like metals, there are many free electrons that can move easily in response to an electric field, making them good conductors of electricity. In insulators, like rubber or plastic, there are few free electrons, so charge carriers cannot move easily, and these materials do not conduct electricity well. In semiconductors, the number of charge carriers can be controlled, allowing for the precise control of electrical conductivity, which is the basis for modern electronics. The movement of charge carriers also plays a critical role in the generation of electromagnetic fields. As charge carriers move through a conductor, they generate a magnetic field around the conductor. This is the basis for the operation of electromagnets and electric motors, where the movement of charge carriers, electrons, generates magnetic fields that can be used to produce force and motion. In fact, the behavior of charge carriers and their interactions with magnetic fields is at the heart of electromagnetism, one of the 4 fundamental forces in nature. One of the most important properties of charge carriers is their mobility. The mobility of a charge carrier refers to how easily it can move through a material in response to an electric field. In metals, the mobility of electrons is typically high, meaning they can move easily through the conductor, resulting in high electrical conductivity. In semiconductors, the mobility of charge carriers can vary depending on the material and its temperature, and this is one of the factors that engineers control when designing semiconductor devices like transistors and diodes. The motion of charge carriers can also be influenced by external factors, such as temperature and impurities in the material. For example, in metals, the presence of impurities can scatter the electrons, reducing their mobility and making the material a poorer conductor of electricity. This is why pure metals, like copper, are better conductors than alloys, which have different atoms mixed in that disrupt the flow of charge carriers. In semiconductors, the presence of impurities can also be used to control the number and behavior of charge carriers, a technique known as doping. By adding small amounts of specific elements to a semiconductor, engineers can create regions of the material that have different electrical properties, which is critical for the operation of devices like solar cells and microchips. In summary, charge carriers are the particles that carry electric charge and allow electric currents to flow. In most materials, electrons are the primary charge carriers, but ions, holes, and other particles can also play this role. The movement of charge carriers is responsible for the behavior of electric currents, and it plays a crucial role in the functioning of everything from electrical circuits to biological systems. Understanding charge carriers is essential for understanding how electricity flows through materials, and it is central to the design of electronic devices, power systems, and many other technologies. Whether we are looking at the behavior of electrons in a wire, the movement of ions in a battery, or the flow of charge in a plasma, charge carriers are the key to understanding the flow of electricity and the workings of the universe itself. The Standard Model of particle physics is one of the most successful theories in all of science, providing a comprehensive framework for understanding the fundamental particles of the universe and their interactions. Within this framework, charge plays a critical role. The Standard Model describes how particles with different types of charge interact through the 4 fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. It's through the lens of the Standard Model that we can understand the role of charge in the behavior of subatomic particles and how these particles come together to form the matter we see around us. At the most basic level, the Standard Model identifies two primary types of charge: electric charge and colour charge. Electric charge, which is the type we're most familiar with in everyday life, is responsible for electromagnetic interactions and governs the behaviour of charged particles like electrons, protons and neutrons. Colour charge, on the other hand, is a property of quarks, the fundamental particles that make up protons and neutrons, and is responsible for the strong nuclear force that binds quarks together inside atomic nuclei. While these two types of charge are different in nature, they are both essential to the interactions that govern the structure and behaviour of matter in the universe. Let's start with electric charge. Electric charge is a fundamental property of particles like electrons and protons. It determines how these particles interact with each other through the electromagnetic force, one of the four fundamental forces of nature. The most familiar manifestation of electric charge is in the form of electric current, where electrons move through conductors to create a flow of charge. In the Standard Model, particles that carry electric charge interact with each other through the exchange of photons, the force carriers of the electromagnetic field. These photons are massless particles that mediate the electromagnetic force, allowing charged particles to exert attractive or repulsive forces on each other, depending on whether their charges are opposite or the same. Electrons, which are fundamental particles, carry a negative electric charge. Protons, which are made up of quarks, carry a positive charge. The interaction between the negatively charged electrons and the positively charged protons is what holds atoms together, allowing atoms to form stable structures and giving rise to all the chemical elements. The electromagnetic force between these charged particles is described by the equations of classical electromagnetism, but the Standard Model takes this further by describing the behaviour of these particles at the quantum level, using quantum electrodynamics, QED. QED is a quantum field theory that explains how charged particles interact with photons, and it provides a mathematically rigorous framework for understanding the electromagnetic force at the level of individual particles. But the role of charge in the Standard Model is not limited to electric charge. The other type of charge that plays a critical role in particle physics is colour charge. Colour charge is a property of quarks, the fundamental particles that make up protons and neutrons. Quarks come in three colours: red, green and blue, which are entirely unrelated to the colours we perceive in visible light. These colours are used as labels to describe the different types of colour charge that quarks can carry. The strong nuclear force, which is responsible for holding quarks together inside protons and neutrons, is mediated by particles called gluons, which exchange colour charge between quarks. In the Standard Model, quarks interact with each other through the exchange of gluons, which are the force carriers of the strong nuclear force. Gluons themselves carry colour charge, which makes the strong force unique among the fundamental forces. Unlike the electromagnetic force, where photons are neutral and don't carry charge themselves, gluons carry colour charge and interact with the colour charge of quarks. The strong force is extremely powerful at the scale of quarks and protons, but it only operates over incredibly short distances. The strong nuclear force is what keeps the quarks bound together inside protons and neutrons, and it's responsible for the stability of atomic nuclei. The distinction between electric charge and colour charge is crucial in the Standard Model, and it helps explain the structure of matter at the most fundamental level. While electric charge governs the behaviour of charged particles like electrons and protons through the electromagnetic force, colour charge governs the interactions between quarks through the strong nuclear force. Together, these two types of charge play a central role in the formation of matter and the interactions that take place inside atomic nuclei. The weak nuclear force, which is another fundamental force described by the Standard Model, also involves interactions between charged particles. However, the weak force is responsible for processes like radioactive decay, where a neutron in an atomic nucleus can decay into a proton, an electron, and an antineutrino. This process, known as beta decay, is mediated by the exchange of W and Z bosons, which are massive particles that carry the weak nuclear force. The weak force is called weak because it is much weaker than the strong nuclear force, but it plays a critical role in the processes that govern the behaviour of subatomic particles, including the fusion of hydrogen into helium inside stars and the decay of unstable particles. The standard model of particle physics also describes how all of these interactions are related through the unification of forces. The electromagnetic force and the weak nuclear force are unified into a single force known as the electro-weak interaction. This unification was one of the key achievements of the Standard Model, and was experimentally confirmed in the 1970s. The discovery of the W and Z bosons at CERN in 1983 provided experimental proof of the electroweak unification, and was a major breakthrough in our understanding of the fundamental forces. In the Standard Model, the forces are mediated by particles known as force carriers. The electromagnetic force is mediated by photons, as we have seen. The strong nuclear force is mediated by gluons, while the weak nuclear force is mediated by the W and Z bosons. The theory also predicts the existence of a fourth force carrier, the Higgs boson, which was discovered in 2012 at CERN's Large Hadron Collider. The Higgs boson is associated with the Higgs field, which is responsible for giving particles their mass. This discovery confirmed a crucial aspect of the Standard Model and marked a major milestone in particle physics. The Standard Model also includes a rich set of particles and interactions that go beyond the well-known electron and proton. It predicts the existence of a variety of subatomic particles, including neutrinos, which are electrically neutral and interact only via the weak nuclear force. Neutrinos are incredibly difficult to detect because they interact so weakly with matter, but they are important for understanding processes like nuclear fusion in stars and the behaviour of certain types of radioactive decay. The Standard Model provides a framework for understanding how all of these particles and forces fit together in a unified picture of the subatomic world. The role of charge in the Standard Model is not just about the interaction of particles through forces, it is also about the fundamental symmetries that govern the universe. The concept of charge conservation, for example, is one of the most important principles in the Standard Model. This principle states that charge can neither be created nor destroyed, only transferred. Whether we are dealing with electric charge or colour charge, the total charge in any given system remains constant, and this conservation is a direct consequence of the symmetries of the fundamental forces. The Standard Model has been incredibly successful in explaining the behaviour of particles and their interactions. It provides a comprehensive and unified theory that has been confirmed by numerous experiments, including the discovery of the Higgs boson. However, the Standard Model is not the final word in our understanding of the universe. It has known limitations such as its inability to explain gravity, the existence of dark matter, or the nature of the quantum vacuum. The search for a more complete theory, such as a theory of quantum gravity or a unified theory of all the fundamental forces, continues to be one of the most exciting challenges in physics today. In summary, the Standard Model provides a framework for understanding the fundamental particles and forces that make up the universe. Charge plays a central role in this framework, governing the interactions between particles through the electromagnetic force, the weak nuclear force, and the strong nuclear force. Electric charge and colour charge are the two main types of charge that dictate how particles interact with each other and form the building blocks of matter. The Standard Model is a powerful tool for understanding the behaviour of the universe at the most fundamental level, and it continues to be a cornerstone of modern physics. Yet, as we push the boundaries of our knowledge, we're reminded that there is still much to discover about the nature of charge and the forces that govern the universe. Antimatter is one of the most fascinating and perplexing concepts in modern physics. It's a form of matter that is essentially the mirror image of regular matter, but with a crucial difference. It carries opposite charge. For every particle that has mass and charge, there exists a corresponding antiparticle that shares the same mass but has the opposite charge. In this chapter, we will explore the relationship between antimatter and charge, examining how antimatter fits into the framework of the Standard Model, how it behaves when it interacts with regular matter, and why its existence raises profound questions about the origins of the universe. At the heart of antimatter is the idea that for every type of particle that makes up regular matter, there is a corresponding antiparticle. An electron, for example, has a negative electric charge. Its antimatter counterpart, the positron, is identical in mass and many other properties, but carries a positive charge. Similarly, a proton, which carries a positive charge, has an antimatter counterpart known as an antiproton, which carries a negative charge. These antiparticles behave in much the same way as their matter counterparts, but because of their opposite charges, they interact differently when they come into contact with regular matter. When a particle meets its corresponding antiparticle, the two annihilate each other in a process known as annihilation. This annihilation releases energy in the form of high-energy photons, typically gamma rays. The annihilation of an electron and a positron, for example, results in the creation of two gamma rays, each carrying the energy that was previously contained in the particles. This energy release is one of the reasons why antimatter is so interesting. It provides a potential source of incredibly efficient energy, as the conversion of matter to energy in annihilation is nearly 100% efficient, in contrast to the relatively inefficient processes we rely on today, such as combustion or nuclear fission. The existence of antimatter was first predicted by Paul Dirac in the 1920s as part of his theory of relativistic quantum mechanics. Dirac's equations described the behavior of electrons moving at high speeds, and they suggested that for every particle like the electron, there should be a corresponding particle with opposite charge. This prediction was confirmed in 1932 by Carl Anderson, who discovered the positron while studying cosmic rays. The discovery of the positron marked the first direct observation of antimatter, and since then, many other antiparticles have been discovered. However, while antimatter exists and can be created in small amounts in laboratories, it is not commonly found in the universe. In fact, the universe seems to be made almost entirely of regular matter, and antimatter appears to be extremely rare. This raises one of the most profound questions in physics. Why is there so much more matter than antimatter in the observable universe? This question is tied to one of the biggest mysteries in cosmology, the problem of the matter-antimatter asymmetry. According to the Standard Model, for every particle created in the early universe, an antiparticle should have been created as well, and the two should have annihilated each other, leaving behind only radiation. This would mean that the universe should be made up of equal amounts of matter and antimatter, with no leftover matter to form stars, planets, or life as we know it. Yet, when we observe the universe, we find that it is almost entirely composed of matter, with very little antimatter to be found. This asymmetry is a key area of research in particle physics and cosmology, and it's one of the reasons why understanding antimatter and charge is so important. To understand the matter-antimatter asymmetry, physicists have proposed several theories. One possibility is that during the early moments of the universe, there was a small imbalance between the amount of matter and antimatter produced. This slight imbalance would have resulted in a small excess of matter, which would have survived the annihilation process, leaving behind the matter-dominated universe we see today. Some theories suggest that this imbalance could be explained by a process known as CP violation, where the laws of physics behave differently for matter and antimatter. CP violation refers to the idea that the symmetry between charge, C, and parity, P, is not perfect in all interactions, meaning that the laws governing the behavior of particles and antiparticles might not be identical in every case. This could help explain why there is more matter than antimatter in the universe, although the exact mechanism remains a topic of ongoing research. In addition to its connection with the matter-antimatter asymmetry, antimatter also plays a crucial role in the study of fundamental symmetries in physics. The fact that antimatter particles have opposite charge to their matter counterparts suggests that charge itself is a fundamental property of particles, one that is not just a simple label, but a deep feature of the laws of physics. When we study antimatter, we are not just studying particles with opposite charge, we are also probing the nature of charge itself and the symmetries that govern the interactions of particles. In particle accelerators, scientists have been able to create and study antimatter in controlled experiments. For example, at facilities like CERN's Large Hadron Collider, LHC, antimatter is produced by smashing high-energy particles together, creating pairs of particles and antiparticles. These antiparticles can then be isolated, studied and analysed. One of the most notable achievements in this area is the creation of antihydrogen, which consists of an antiproton and a positron. By studying antihydrogen, physicists can gain insight into the behaviour of antimatter under controlled conditions and investigate whether antimatter obeys the same laws of physics as matter. This is particularly important in the context of testing the fundamental symmetries of physics, such as the symmetry between matter and antimatter, and understanding how the two interact. Another important area of research involves the potential use of antimatter in energy production and propulsion. As we mentioned earlier, when matter and antimatter annihilate each other, the process releases energy in the form of high-energy photons. This energy release is incredibly efficient, making antimatter an ideal candidate for advanced propulsion systems, particularly for space exploration. Theoretical proposals have suggested that antimatter could be used as a fuel source for spacecraft, allowing for faster travel across vast distances in space. However, producing and storing antimatter is currently an enormous challenge, as antimatter is expensive to produce and difficult to contain. Despite these challenges, the potential applications of antimatter are tantalizing and could revolutionize energy production and space exploration if technological advancements can make antimatter more accessible. Antimatter also plays a key role in medical technologies, particularly in positron emission tomography, PET scans. PET scans are used to detect and diagnose various diseases, including cancer, by injecting a small amount of radioactive material into the body. This material emits positrons, which then interact with electrons in the body, leading to annihilation and the release of gamma rays. By detecting these gamma rays, a PET scan can create detailed images of the inside of the body. This is just one example of how antimatter and the interaction between charge and antimatter can have practical applications in medicine and other fields. In summary, antimatter is the mirror image of regular matter, consisting of particles that carry opposite charge to their corresponding matter particles. When matter and antimatter meet, they annihilate each other, releasing energy in the process. Antimatter plays a crucial role in understanding the fundamental laws of physics, particularly in relation to charge, symmetry, and the matter-antimatter asymmetry. While antimatter is rare in the universe, scientists have been able to create and study it in particle accelerators, and it holds great potential for future technologies, from energy production to space travel. Understanding antimatter and its relationship to charge is essential for advancing our knowledge of the universe and unlocking new possibilities for the future. Charge is one of the fundamental properties of matter, and its significance extends far beyond the scope of electrical interactions in everyday life. In fact, charge is at the very heart of the structure and behaviour of the universe. From the formation of atoms to the dynamics of galaxies, charge plays a crucial role in shaping the cosmos as we know it. In this chapter, we will explore why charge matters in the universe, examining how it influences everything from the tiniest particles to the largest structures in the cosmos, and how it governs the forces that shape the universe. At the most basic level, charge is the reason why matter exists in its current form. The interactions between charged particles, particularly the attraction between electrons and protons, are what hold atoms together. Without the electromagnetic force generated by these interactions, atoms would not be stable, and the universe as we know it would not exist. The electric charge of the proton is what keeps the electron in orbit around the nucleus, and it is this very interaction that gives rise to all the chemical elements. These elements, in turn, are the building blocks of everything from the air we breathe to the stars that shine in the night sky. In addition to holding atoms together, charge also governs the behaviour of atoms and molecules. The arrangement of electrons in atoms determines how atoms interact with each other and how they bond to form molecules. Chemical reactions, the foundation of biology and much of the material world, occur because of the way charged particles interact. When atoms bond, they do so by sharing or transferring electrons, and these interactions are driven by the electric force between the charged particles. Charge is the invisible force that dictates how substances combine and transform, forming the materials, substances and energy that we encounter every day. Beyond atoms and molecules, charge also plays a critical role in the functioning of biological systems. For example, in nerve cells, the movement of charged ions across cell membranes generates electrical signals that are essential for transmitting information throughout the body. These signals allow us to sense the world around us, move our muscles, and think. The brain, in particular, relies on the movement of charged particles to process and transmit information. Without the movement of ions and the creation of electrical potentials, the intricate networks of neurons that make up our nervous system would not function, and life, as we know it, would not be possible. Charge also underpins many of the forces and phenomena that govern the larger scale behaviour of the universe. The electromagnetic force, which is responsible for the interactions between charged particles, is one of the four fundamental forces in nature. While it is much weaker than the strong nuclear force and gravity, it is still incredibly important for shaping the behaviour of matter. The electromagnetic force is responsible for the formation of electric and magnetic fields, which govern everything from the behaviour of light to the dynamics of charged particles in space. For example, the behaviour of light itself is governed by the interaction of electric and magnetic fields. Light is an electromagnetic wave, meaning it consists of oscillating electric and magnetic fields that travel through space. The electromagnetic spectrum, which includes everything from radio waves to gamma rays, is a direct result of the way charge interacts with electric and magnetic fields. Without the properties of charge, there would be no light, no radio waves, no microwaves. Essentially, the entire electromagnetic spectrum would not exist. The importance of charge extends to even larger cosmic scales. The magnetic fields of planets, stars, and galaxies are the result of charge and its interactions with other charged particles. The Earth's magnetic field, for example, is generated by the motion of charged particles in the planet's core, and it plays a crucial role in protecting the planet from harmful solar radiation. The solar wind, a stream of charged particles emitted by the sun, interacts with the Earth's magnetic field to create the auroras or northern and southern lights. These spectacular displays of light are the result of charged particles from the sun colliding with the Earth's atmosphere, releasing energy in the form of visible light. Similarly, the sun's magnetic field governs the behaviour of the solar system. The sun's magnetic activity, such as solar flares and coronal mass ejections, can have significant effects on space weather, influencing the behaviour of charged particles in space and even disrupting communication systems on Earth. The sun's magnetic field is also responsible for the solar wind, which interacts with the Earth's magnetic field and influences the shape and behaviour of Earth's magnetosphere. On an even grander scale, charge plays a role in the formation and evolution of galaxies. The gravitational force that holds galaxies together is influenced by the presence of charged particles, and the movement of these particles can contribute to the dynamics of the galaxy. For example, the charged particles in the interstellar medium can generate magnetic fields that influence the motion of gas clouds, stars, and other celestial objects. Charge is also a key component of the energy processes that drive the formation of stars and the evolution of galaxies. In the realm of cosmology, charge is also important for understanding the behaviour of the early universe. In the moments following the Big Bang, the universe was filled with a hot, dense plasma of charged particles. As the universe expanded and cooled, these particles began to combine, forming the first atoms and eventually the first stars and galaxies. The behavior of charge during this early period of cosmic evolution set the stage for the formation of the universe as we know it today. In addition to its role in the large-scale structure of the universe, charge also has profound implications for our understanding of fundamental physics. The unification of the electromagnetic force and the weak nuclear force into the electroweak interaction is one of the great achievements of modern physics. This unification shows that, at high energies, the distinction between the electromagnetic force and the weak nuclear force disappears and they become a single force. This discovery, which was confirmed by experiments at CERN, has helped to deepen our understanding of the fundamental forces in nature and has led to new insights into the early moments of the universe. Charge is also central to the search for new physics beyond the Standard Model. The Standard Model describes the behavior of particles and forces, but it leaves open many important questions, such as the nature of dark matter and the behavior of gravity at the quantum level. The study of charge and its interactions is crucial for understanding these mysteries and for developing new theories that may help explain the fundamental nature of the universe. One of the most intriguing aspects of charge is its connection to symmetry and conservation laws. The law of charge conservation states that the total charge in a closed system remains constant over time. This principle, which has been experimentally verified in countless experiments, is a direct consequence of the symmetries of the universe. The conservation of charge is a powerful tool for understanding the behavior of particles and forces, and is one of the cornerstones of modern physics. It is a reminder that charge is not just an arbitrary property of matter, but a fundamental feature of the universe that governs the way particles interact with each other. In summary, charge is a fundamental property of matter that plays a central role in shaping the universe. From the formation of atoms to the behavior of galaxies, charge governs the interactions that give rise to the physical world. It influences the forces that hold matter together, drives the behavior of light and electromagnetic radiation, and plays a crucial role in the dynamics of celestial bodies. Charge is also essential for understanding the fundamental forces of nature and for exploring the mysteries of the universe. Whether we are looking at the behavior of particles in a laboratory or the evolution of the cosmos, charge matters because it is one of the key factors that shapes the world we live in. Dark matter is one of the greatest mysteries in modern physics and cosmology. Despite its name, dark matter is not actually dark in the sense of being invisible or unobservable. In fact, it doesn't emit, absorb, or reflect light, which is why it's invisible to the electromagnetic spectrum. However, it has a significant gravitational effect on visible matter, influencing the formation of galaxies, galaxy clusters, and the structure of the universe as a whole. In this chapter, we will explore the relationship between charge and dark matter, examining whether dark matter has any charge, how it interacts with regular matter, and how understanding charge could help us uncover the nature of dark matter. First, let's understand what we do know about dark matter. Although dark matter has never been directly detected, its existence is inferred from its gravitational effects on visible matter. Observations of galaxies and galaxy clusters show that there is much more mass present than can be accounted for by the visible matter, such as stars, gas, and dust, that we can observe through telescopes. The gravitational pull from this unseen mass causes galaxies to rotate faster than would be expected based on the visible matter alone. Additionally, dark matter helps explain the way galaxies move within clusters, as the observed gravitational effects would be impossible to reconcile with the amount of visible mass in these clusters. These observations suggest that dark matter makes up about 27% of the universe's total mass energy content, while visible matter, including stars and planets, accounts for only about 5%. One of the key properties of dark matter is that it does not interact with electromagnetic radiation, meaning it does not emit, absorb, or reflect light. This makes dark matter completely invisible to conventional observational methods, which rely on detecting electromagnetic waves such as light, radio waves, or X-rays. This lack of electromagnetic interaction is one of the defining characteristics of dark matter and suggests that it does not carry electric charge in the same way that regular matter does. However, while dark matter is thought to be electrically neutral and non-interacting with electromagnetic fields, its existence and behaviour are still closely tied to fundamental forces, and charge may still play a role in understanding its properties. If dark matter is electrically neutral, as many theories suggest, it would not interact with ordinary matter through the electromagnetic force, which is the force responsible for most of the interactions between charged particles. This would mean that dark matter particles, if they exist, do not have electric charge, and they do not participate in the same interactions that govern the behaviour of charged particles, such as the movement of electrons or the formation of chemical bonds. Instead, dark matter is thought to interact primarily through gravity, and possibly the weak nuclear force, which is the force responsible for radioactive decay and some particle interactions at the subatomic level. But while the prevailing theory is that dark matter is electrically neutral, this is not to say that it cannot interact with charge in some indirect way. One of the possibilities that scientists are exploring is the existence of dark matter particles that might carry a form of charge, albeit a very different kind of charge from the familiar electric charge. For example, some theories propose that dark matter particles could possess a form of dark charge that interacts with other dark matter particles or with dark energy, but not with ordinary matter. This concept of dark charge is still highly speculative, but it highlights the possibility that dark matter could have a deeper connection to the concept of charge than we currently understand. Another possibility is that dark matter could interact with regular matter via the weak nuclear force, but this interaction would be very weak and difficult to detect. The weak nuclear force is responsible for processes like beta decay, and it is much weaker than the electromagnetic force. If dark matter particles interact with ordinary matter through the weak force, they would not produce the same electromagnetic effects as regular charged particles, but they could still be detected by their gravitational effects or through high-energy particle interactions. Some proposed dark matter candidates, such as weakly interacting massive particles, WIMPs, are thought to interact with ordinary matter in this way, although no direct detection of WIMPs has yet been made. One of the most intriguing aspects of dark matter is its apparent clumpiness in the universe. Dark matter is not evenly distributed, but rather forms structures that influence the formation of galaxies and galaxy clusters. This clumping suggests that dark matter may have some form of self-interaction or interaction with other dark matter particles, which could help explain its behaviour and distribution. If dark matter does interact through forces other than the electromagnetic force, it could provide important clues as to the nature of charge in the dark sector of the universe. There are also some theories that propose the existence of hidden sectors in which dark matter particles might interact with each other via forces that do not involve electromagnetic radiation, but could still be related to charge in a broader sense. For example, the hidden photon theory suggests that dark matter might interact with a form of light that does not interact with ordinary matter in the same way as visible light. This hidden photon could be a mediator of the forces between dark matter particles, similar to how the photon mediates the electromagnetic force between charged particles. While this idea is still speculative, it provides a potential avenue for understanding how charge could play a role in dark matter interactions. Despite these intriguing possibilities, the most widely accepted theory is that dark matter does not carry electric charge in the same way that regular matter does. Its lack of interaction with electromagnetic radiation makes it a ghostly presence in the universe, detectable only through its gravitational effects. However, the fact that dark matter interacts with gravity means that it is intrinsically tied to the fabric of space-time, and its behaviour is crucial for understanding the large-scale structure of the universe. Without dark matter, galaxies would not have the mass required to hold themselves together, and the formation of galaxy clusters would look very different. Understanding how dark matter interacts with gravity and its possible connections to other fundamental forces is one of the key challenges in modern cosmology and particle physics. The search for dark matter is ongoing, with numerous experiments being conducted to detect its presence directly. These experiments include attempts to capture dark matter particles in underground detectors, such as the Large Hadron Collider at CERN, and the detection of unusual gravitational effects that could be attributed to dark matter. Despite the challenges, scientists are optimistic that new breakthroughs in technology and theory will eventually reveal the true nature of dark matter. In summary, while the prevailing view is that dark matter is electrically neutral and does not interact with the electromagnetic radiation in the same way as regular matter, the possibility remains that dark matter could be related to charge in some indirect or hidden way. Its lack of interaction with visible light and electromagnetic forces makes it one of the most elusive and mysterious components of the universe. However, its gravitational effects on galaxies and large-scale cosmic structures are undeniable, and its study is crucial for our understanding of the universe's origins and evolution. By exploring the relationship between charge and dark matter, we may uncover new insights into the fundamental nature of matter, energy, and the forces that govern the cosmos. Charge is one of the most fundamental aspects of the universe, shaping the way matter interacts, behaves, and exists. While the concept of charge might seem abstract in some contexts, it is directly responsible for some of the most critical technologies that power our world today. From electrical power systems to communication technologies, medical devices, and even transportation systems, the manipulation of charge is the driving force behind a vast array of real-world applications. In this chapter, we will explore how charge is harnessed and utilized in various practical technologies and systems, highlighting the essential role it plays in our everyday lives. One of the most well-known and widespread applications of charge is in the generation and distribution of electricity. Electricity is essentially the flow of electric charge through conductors, usually electrons moving through a wire. In power plants, energy is used to move electrons through conductors to generate electric currents. These currents are transmitted through power lines to homes, businesses, and industries, powering everything from lights and appliances to industrial machinery. The efficiency with which charge can be manipulated and transmitted allows for the widespread distribution of electricity over vast distances. Power grids, transformers, and substations all rely on the controlled movement of charge to ensure that electricity reaches its destination safely and efficiently. In addition to its role in electrical power distribution, charge plays a central role in the world of electronics. Almost every modern electronic device, from smartphones to computers, relies on the flow of charge through circuits to function. Semiconductors, materials that can conduct charge under specific conditions, are the backbone of modern electronics. By carefully controlling the flow of charge in semiconductors, engineers have developed transistors, the tiny switches that allow for the processing and transmission of information in electronic devices. These transistors are used to perform calculations, store data, and run software, making everything from your computer to the global internet infrastructure possible. One of the most critical technologies that rely on charge is batteries. Batteries store electrical energy in the form of chemical energy and release it as electric charge when needed. The flow of charge through the battery circuit powers a wide range of devices, including everything from flashlights to laptops to electric vehicles. The efficiency, longevity, and capacity of a battery are determined by how effectively it can move charge between its positive and negative terminals. The development of advanced batteries, such as lithium-ion batteries, has enabled the widespread adoption of portable electronics and electric vehicles, transforming industries and everyday life. As the demand for renewable energy storage grows, the ability to store and release charge efficiently through batteries will play a critical role in future energy systems. Charge is also central to a variety of medical technologies. In medicine, Electrical signals and the flow of charge are used in diagnostic tools, therapeutic devices, and imaging technologies. One of the most important medical applications of charge is in positron emission tomography, PST scans. PET scans use a small amount of radioactive material, which emits positrons, the antimatter counterpart of electrons. When a positron interacts with an electron, they annihilate each other, producing gamma rays that can be detected by the PET scanner. This allows doctors to create detailed images of the inside of the body, helping to diagnose conditions such as cancer and neurological disorders. PET scans are an essential tool in modern medicine, providing doctors with non-invasive ways to examine the body in high detail. Another important medical use of charge is in the operation of defibrillators, which are used to restore normal heart rhythms in patients experiencing cardiac arrest. A defibrillator delivers a high-voltage electrical shock to the heart, using the movement of charge to reset the electrical signals that control the heartbeat. The ability to manipulate charge with such precision in medical devices has saved countless lives and continues to be a critical part of emergency care. In addition to diagnostics and treatment, charge is central to various therapeutic devices used to stimulate nerves and muscles. For example, transcranial magnetic stimulation, TMS, uses rapidly changing magnetic fields to influence the electrical activity in the brain. This technique is used to treat conditions such as depression and to study brain function. Similarly, electrical stimulation is used in physical therapy to promote muscle recovery and healing by applying controlled electrical impulses to stimulate muscles and nerves. Charge is also fundamental to communication technologies, particularly wireless communication. The ability to transmit data through electromagnetic waves relies on the movement of charge. For example, when an alternating current flows through an antenna, it generates electromagnetic waves that travel through space, carrying information such as sound, video, and data. This principle underlies technologies like radio, television, and Wi-Fi, enabling us to connect and communicate over vast distances. The ability to harness charge in this way has revolutionized the way we interact with the world, allowing for instantaneous communication and information sharing across the globe. The application of charge also extends to transportation systems, particularly in the field of electric vehicles, EVs. Electric vehicles rely on the movement of charge within batteries to power an electric motor, which drives the vehicle's wheels. Unlike internal combustion engines, which burn fuel to produce energy, EVs use the movement of charge through an electric circuit to produce mechanical motion. This technology is transforming the automotive industry, providing a cleaner, more efficient alternative to traditional gasoline-powered vehicles. The ability to manipulate charge in electric vehicles has the potential to reduce carbon emissions, improve energy efficiency, and reduce our reliance on fossil fuels. Another fascinating application of charge is in the field of magnetic levitation, maglev trains. These high-speed trains use powerful magnets to levitate above a track, reducing friction and allowing the train to travel at extremely high speeds. The magnetic fields required for maglev trains are created by the movement of charge through electromagnets. By precisely controlling the flow of charge in these magnets, engineers have been able to develop transportation systems that are faster and more efficient than conventional trains. Charge is also central to the technology behind various lighting systems. In incandescent bulbs, charge flows through a filament, heating it up until it emits light. In more efficient systems like light-emitting diodes, LEDs, the flow of charge through a semiconductor material causes it to release energy in the form of photons, producing light without generating much heat. This energy-efficient use of charge has made LEDs the preferred lighting technology in many applications, from household lighting to large-scale streetlights. The movement of charge in these materials has enabled us to create brighter, more efficient and longer-lasting lighting solutions. In the realm of space exploration, charge is used in a variety of ways. For example, ion propulsion systems use electric charge to accelerate ions, creating thrust that propels spacecraft. These systems are much more efficient than traditional chemical rockets and have the potential to enable long-duration missions to distant planets and beyond. The ability to manipulate charge in such a precise way opens up new possibilities for space exploration, potentially making interplanetary travel more feasible in the future. The diverse applications of charge are a testament to its fundamental importance in the physical world. From the basic functioning of atoms to the technologies that power modern life, charge is at the heart of many processes and systems that we take for granted. As technology continues to advance, our understanding of charge and its manipulation will only become more refined, leading to new innovations and possibilities that we may not yet even fully comprehend. Whether it's through the generation of electricity, the development of medical devices, or the exploration of space, charge continues to shape the world in ways both big and small. As we look toward the future, the ability to control and harness charge will be at the core of new technologies aimed at addressing some of the world's most pressing challenges. Whether through the development of renewable energy systems, advancements in communication networks, or breakthroughs in medicine and transportation, charge will remain a key driver of progress. The study and application of charge are fundamental to our understanding of the universe, and they will continue to guide scientific discovery and technological innovation for generations to come. Charge is a concept that runs through every corner of the physical world. It's not just a theoretical abstraction confined to the pages of textbooks. It's the force that governs the behavior of particles, the foundation of the electromagnetic force, and the key to understanding the interactions that make up matter itself. From the flow of electricity in your devices to the formation of the universe's largest structures, charge is the unseen driver of nearly every process we encounter. It influences the smallest particles in atoms, the behavior of light, and even the movement of galaxies. Yet, despite its omnipresence, the true nature of charge remains a profound mystery in many ways. At the most basic level, we understand charge as a fundamental property of matter. It's what allows particles like electrons and protons to interact with each other through the electromagnetic force, which in turn governs everything from chemical reactions to the behavior of light. The fundamental rule that like charges repel and opposite charges attract provides the foundation for our understanding of electromagnetism and is responsible for the stability of matter itself. Without charge, atoms would not form, molecules would not bond, and life as we know it could not exist. In this sense, charge is one of the pillars that supports the entire structure of the universe. Despite its importance, charge is an abstract concept that is not fully understood in the way that other properties of matter, like mass, are. We can describe the behavior of charged particles with great precision, and we can measure the forces between them using equations like Coulomb's law, but the essence of what charge truly is remains elusive. Charge doesn't have a known underlying cause or mechanism that we can directly observe in the same way we observe the effects of mass or gravity. In this respect, charge is more of a property than a substance. It's not something that we can see, touch, or isolate in the way we can with matter. It's a feature that dictates how particles behave and interact with one another. At the quantum level, charge takes on an even more mysterious character. The interactions between charged particles are governed by the exchange of photons, the force carriers of the electromagnetic field. These interactions are described by quantum electrodynamics, QED, which is a highly successful theory that explains how charged particles exchange photons and how this gives rise to the electromagnetic force. QED has been tested with extreme precision and has passed every experimental test, but it still leaves many questions unanswered. For example, the true nature of photons and the mechanism by which they mediate the force between particles is still a subject of debate and research in the field of quantum mechanics. Moreover, the connection between charge and other fundamental forces is still not fully understood. While we have made great strides in understanding how charge interacts through the electromagnetic force, we still don't have a complete theory that unifies all four fundamental forces: gravity, electromagnetism, the weak nuclear force and the strong nuclear force, into a single framework. Charge, as we understand it, plays a central role in the electromagnetic force, but we still don't know how it might relate to the other forces. The search for a unified theory of everything, often referred to as the theory of everything, TOE, is one of the biggest goals of modern physics. Some theories, such as string theory, attempt to describe all forces as manifestations of a deeper underlying reality, but these ideas are still speculative and have yet to be experimentally verified. The mystery of charge also extends to the role it plays in the universe at large. For example, charge is central to the formation of atoms and molecules, which in turn form the building blocks of matter. The balance between positive and negative charges in atoms is what gives rise to chemical bonds, allowing for the formation of complex molecules that make up the materials we interact with every day. Yet despite our understanding of these processes, we don't know why charge behaves the way it does, why particles like electrons and protons carry charge, or why there is such a thing as positive and negative charge at all. Charge is an essential feature of matter, but its origin and deeper nature remain mysterious. One of the most profound questions related to charge involves the behaviour of antimatter. Antimatter, as we've discussed, consists of particles that have opposite charge to their matter counterparts. For example, a positron is the antimatter counterpart of an electron and carries a positive charge, while an antiproton carries a negative charge and is the antimatter counterpart of the proton. When matter and antimatter meet, they annihilate each other, releasing energy. But the existence of antimatter raises deep questions about the nature of charge and the symmetry of the universe. According to the standard model of particle physics, for every particle with charge, there should be an equivalent antiparticle with the opposite charge. Yet, for reasons we don't fully understand, the universe seems to be made almost entirely of matter, with very little antimatter. This imbalance, known as the matter-antimatter asymmetry, is one of the biggest unsolved mysteries in physics. Why is there so much more matter than antimatter? And what does this tell us about the true nature of charge and the fundamental symmetries of the universe? Charge also plays a crucial role in cosmology, influencing the formation and evolution of the universe. In the early moments of the Big Bang, the universe was filled with a hot, dense plasma of charged particles. As the universe cooled and expanded, these particles combined to form atoms, leading to the formation of galaxies, stars, and all the matter we observe today. The interactions between charged particles in this early universe set the stage for the structure of the cosmos, and the behaviour of charge continues to shape the evolution of galaxies and stars. For example, the magnetic fields of stars and galaxies are generated by the motion of charged particles in plasma, and these magnetic fields influence the behaviour of charged particles in space, affecting everything from the solar wind to the formation of cosmic structures. In addition to its role in the large-scale structure of the universe, charge is also central to the behaviour of light and electromagnetic radiation. Light itself is an electromagnetic wave composed of oscillating electric and magnetic fields. The fact that light consists of these two intertwined fields is a direct consequence of the behaviour of charge. The study of electromagnetic waves has led to some of the most profound discoveries in physics, including the unification of electricity and magnetism into the theory of electromagnetism, the development of quantum mechanics, and the discovery of the nature of light itself. Despite all that we have learned about charge, there is still much we don't know. While we have a detailed understanding of how charge behaves and how it interacts with other particles, the fundamental nature of charge, what it is, why it exists, and why it behaves the way it does, remains one of the deepest mysteries in physics. The search to answer these questions is at the forefront of scientific inquiry, and it drives much of the research in both particle physics and cosmology. As we continue to probe the mysteries of charge, we may uncover new insights into the structure of the universe and the forces that govern its behaviour. Whether through the study of antimatter, the search for a unified theory of forces, or the investigation of the early universe, the study of charge will continue to shape our understanding of the cosmos. The mystery of charge, though profound, is also a powerful driving force in our quest to unlock the secrets of the universe. In the end, charge remains a fundamental piece of the puzzle that makes up the physical world. Its behavior dictates the interactions between particles, governs the forces that shape matter, and influences the structure and evolution of the universe. Though we have made incredible strides in understanding charge and its role in the universe, we're only beginning to scratch the surface of its true nature. The deep mystery of charge continues to inspire curiosity, exploration, and discovery, and it promises to be a central focus of scientific inquiry for years to come.